Okay, so for problem number 7, focusing immediately on what they're asking for, what is the perimeter in meters of DEF? So this is a perimeter problem. That's the first thing to make a note of. You might even want to underline that, in the test booklet. But we have ABC, which is 6, 6, and 10. We also have DEF over here, which is 3 and 5. And then we have this sort of missing side length here. And we want the perimeter of this one. So we know that the answer already, in fact, you might want to write this equation right out the gate. The answer is going to be x plus 3 plus 5, which simplifies to x plus 8. So clearly we would have the answer. We'd have the perimeter of this thing if we knew what x was, because then we could just add it to 8, and then we'd be done. So our first goal is to find x. Well, the bottom line is these triangles are similar, which means that the angles correspond with each other. Now, before we get into that, let's just be very clear about something else. This is an isosceles triangle because you have these two side lengths that are the same. So we know that these angles correspond with each other, angle A and angle C, because of the base angles. And then you have this other obtuse angle right here. Now, in the test booklet, it says triangle ABC and DEF are similar, and those capital letters like A, B, and C should correspond with D, E, and F in such a way that angle A corresponds with angle D, angle B corresponds with angle E, angle C corresponds with angle F. So the order with which they write the letters to denote each triangle matters. Okay, so what I mean by that is, this angle A is most definitely going to be the same angle measure as angle D. All right, so I'm going to do a single rainbow there. Angle B corresponds with angle E because it's the second letter in that sequence. And angle C corresponds with angle F. And when I say corresponds, more specifically, it's congruent to angle F. It's the same measure. Then we can clearly say, okay, well, this is clearly an isosceles triangle where the shorter side lengths are equal, and the third side length is longer. Well, that would make x be 3, because we have our own isosceles triangle here where the shorter side lengths are equal, and the third side length is longer, right? So x is 3. So we could write 3 plus 8, and that of course equals 11, which is the answer C. Okay, so for problem number 13, the final question they're asking is, what is the area in square inches of the aluminum foil that is exposed on the top surface of the cardboard? Well, that is a classic, sometimes referred to as a donut problem, where you have some larger shape and you have some smaller shape within it, but what you're really looking for is the area of this section all the way around. Okay, so I'm actually going to model this by saying that the answer is going to be the area of the larger shape minus the area of the smaller shape, and that's going to give us the answer. Okay, because if we did the area of the black rectangle, subtracted the area of the red rectangle, we would be left with this border here. So that's the answer. Area of the black rectangle minus the area of the red rectangle would give us the answer. So then it leads to the question of, well, what is the area of the black rectangle, and what's the area of the red rectangle? Because if we had those, then we'd be essentially done. Well, the red rectangle, that area is given. And notice how we're dismissing the height of 3 inches in this case. We only need to pay attention to the 16 by 12 inch aspect. We only need to pay attention to 16 by 12. Okay, because we're looking at an overhead view. We are only concerned with the area of the aluminum foil that's exposed on the top surface. So we're not really caring about height in this case. We're looking only from a bird's eye view down at this thing. And that is very nice to know, because then we could just clearly do 16 times 12 there and get 192. So then, of course, the question is, what is the area of this black larger rectangle? Well, you look at the clues that they give you. Well, apparently, this person used a piece of cardboard large enough to allow the cardboard to extend 2 inches beyond the cake of all sides, or on all sides. So we can imagine that scenario where this is 12 and this is 16. So if it's 2 inches beyond the cake on all sides, well, this right here would be 2 inches. This right here would be 2 inches. This right here would be 2 inches. And this right here would be 2 inches. And then we could ask ourselves, okay, well, what's that and what's that? Well, this is clearly 12, because you could imagine the red piece overlaying. Well, that section's 12, 2 inches on one side, 2 inches on the other. This section right here is 16, corresponding with that, and it's going to be 2 inches there, 2 inches there. So I'm going to write 16 there. So when analyzing what the actual dimensions of the rectangle is, you could most definitely say that this one is going to be 20, because 16 plus 2 plus 2 is 20. And as far as the total side length for that, that's going to be 12 plus 2 plus 2 is 12 plus 4, which is 16. So the area for this rectangle is, 20 times 16, which is 320. So at the end of the day, what we're really doing is 320 minus 192, and that is 128. 128, and that is in the answers. It's always a good sign when you see the answer you came up with in the multiple choice options. It's E. So the final question for problem number 14 is, what is the number of pieces the principal cut the cake into? Okay, now quickly I'll just sort of draw the cake itself. This is clearly a three-dimensional figure. That's 3, that's 16, this right here is 12. And apparently the teacher, or the principal rather, is cutting the cake into pieces where each piece is 2 inches wide, 2 inches long, and 3 inches high. So we're looking at something like this, where it's 3, and then it's 2 by 2. And here's the top portion, okay? Now, I want to just draw everyone's attention to the fact that this height corresponds with this height, okay? So you could imagine maybe one of the pieces is like that, where it's clearly up by 3, and then it's like this, where that's 2, and that's 2 right there, okay? And we want to know how many of these pieces can we cut from the whole cake, essentially. And it's important to recognize that you could actually disregard the height. you could think of it as like, okay, well, the height is corresponding, so that's fine, right? Then really all we need to do is pay attention to the dimensions of length and width. We could just do an overhead view and just see how many of these squares, we could cut this cake into. And let's do an overhead shot of the rectangular cake. Do a little divider line here. Overhead shot where we have 16 by 12 right there. And we essentially want to know, well, how many of these 2 by 2 squares, really, could we cut out of this whole thing? Well, the good news is that's just going to be the larger area, which we already discovered before was 192, I believe. That's going to be the larger area divided by the smaller area, which is 4. Because if you want to know how many of these like 2 by 2 cubes fit inside this larger area, well, that's ultimately a division problem. So it's going to be the larger area, I'll call it A sub L, divided by the smaller area, which is A sub S, and that's going to be our answer. So what is the larger area? Well, the larger area is most definitely going to be 16 times 12, and that is 192. 192, and that's going to be divided by the smaller area of each of these little squares, which is 4. And 192 divided by 4 is 48, which is answer choice J. Boom. Piece of cake. No pun intended, actually. Okay, so the final question they ask here is really the entire problem. It's what is the y-intercept of the line in the standard xy coordinate plane that goes through the points, blah, 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 blah. So the y-intercept should make everybody think about this form of a line. It should at least, remind people of this form. This is called the slope-intercept form, where, m is the slope of a line and b is the y-intercept. So really, what we're trying to find out in this problem is what is b? Okay, if we were to put this line in slope-intercept form, what would be b? Okay, so they give us clues. It's kind of a classic algebra problem, to be honest. You've got -3, 6 is a point that this line goes through. Another point this line goes through is 3, 2. Now, most students watching this probably have learned that you could absolutely use the slope formula to figure out at least the slope, and that would get us closer to figuring out the y-intercept, okay? If we could find the slope, we'd get a little bit closer to figuring out the y-intercept. So the slope formula itself is y2 minus y1 all over x2 minus x1. Definitely something you should know for the ACT. This is x1, y1. We'll call this x2, y2. Some of you at home might be wondering, could I have called -3, 6 x2, y2 and 3, 2 x1, y1? And the answer is yes. You just pick one of the points to call x1, y1. Just do that first. I don't care which one it is, but go ahead and do it. Once you pick that point, definitely call the other one x2, y2, and everything will work out in the end. So I'm big on parentheses, so I'm going to do parentheses minus parentheses, because I know it's going to be something minus something else, all over something minus something else. Then I fill it in after that. So it's going to be y2 minus y1. Well, that's going to be 2 minus 6. And then it's going to be x2 minus x1, and that's going to be 3 minus -3. Now, by the way, this is why I do, as a reminder, it's why I do the parentheses, because I want to clearly see whether or not I'm subtracting a negative, and in this case I am. It might have been harder to see that if I didn't use parentheses, because maybe this minus sign would have blended into this minus sign, and I would have fooled myself into thinking that this is 3 minus 3. It's not 3 minus 3, it's 3 minus -3, which is completely different. So this would turn into 2 minus 6 is -4, and 3 minus -3 is really 3 plus 3, which is 6, and that most definitely reduces even further to -2/3. So we have our slope now, -2/3. So what I'm going to do is sort of rewrite or write the line up here with the information that we've gathered. And we have y equals -2/3, x, don't forget the x, plus b. Now we're still trying to figure out what b is though, right? I mean, that's the original situation that we are attempting to solve because that's what they're asking for. They want b. Well, what do? Well, some of you may remember from algebra class, one very common method is to just pick one of these points. It actually doesn't matter which one, and you just work with it. And I'm going to pick this one because it's got positive numbers in it. We could have used this one, but let's pick this one because positive numbers are a little bit easier, for me at least, to think about. And what we're going to do is we're going to substitute 2 in for y and 3 in for x, and then we're just going to solve for b. That's all you got to do. So instead of y, I'm going to write empty parentheses. Okay, instead of x, I'm going to write empty parentheses, and then we have our b just hanging out, minding its own business. So y is 2, and x is 3, and therefore on the next line, I could most definitely write 2 equals, okay, let's analyze this, -2/3 times 3. These 3's cancel out. There's a cross cancellation that can take place there, which is amazing. And then we are going to have, as a result, -2 times 1, because these cancel. That turns into a 1. That turns into a 1. So it's just -2 times 1, which is just -2 plus b. In order to solve for b, I would add 2 to both sides. Easy enough. We end up with b equals 4. And that actually is the answer. I mean, if I was to rewrite the equational line, it would say y equals -2/3 x plus 4. But at the end of the day, we know that we're trying to figure out what b is because we paid attention to what the problem is asking for, and we are done. b equals 4, end of story, case closed, and that is most definitely answer choice H. So for problem number 17, ultimately the final question they're asking is what is the distance in inches between the centers of the two holes in the machine heart? So basically, this relies on your ability to notice that, the entire length across is 11 5/8, and we've got this scenario here, and we know that from here to here, from here to about there, and from here to there, we have measurements there. We've got 2 and 1/16 there, we got 4 3/4 there. I'm actually just going to write it down here because I have a little bit more room. So we have 2 and 1/16, and we have 4 3/4. And we're looking for, okay, well, what is, this distance here? So we'll call that x, okay? We're trying to find x. That's what we're trying to do. And hopefully at home, students at home can see, well, this is really just easily modeled by an algebraic equation that says this length plus x plus this length is going to equal the whole length, right? So I'm just going to write that because that gets us certainly one step closer to the answer. So we have 2 and 1/16 plus x plus 4 and 3/4, and that's going to equal 11 and 5/8. Now, many of you might be wondering, well, what do I do with all these mixed numbers? This is a ridiculous situation, okay? And I agree, it's kind of ridiculous. But the good news is it's going to be smart to turn these into improper fractions. So just rely on your ability to turn these numbers into improper fractions. So for example, 2 and 1/16, if we were to turn that into an improper fraction, well, that would be 16 times 2 plus 1. 16 times 2 plus 1, which is 33 over 16. Okay, so that's actually 33 over 16. X is still just X. And then we have this one. 4 times 4 is 16, plus 3 is 19. So that's going to be 19 over 4. And then that's going to equal, let's see, 8 times 11 is 88, plus 5 is 93 over 8. Okay, now we have ugly improper fraction, improper fraction, improper fraction here. We got X over here. It would be nice to combine these two, right? And then we could subtract it and solve for X, right? I mean, that'd be nice. But the problem is we have these denominators that are annoying, okay? These are clearly annoying denominators. So a great trick of the trade to get rid of annoying denominators is figure out what is the LCD, what is the hypothetical LCD, least common denominator, that we would choose if we were to try to add all these together or subtract them or whatever. What would be the common denominator? Well, that's always going to be the least common multiple of 16, 4, and 8. What is the least common multiple of 16, 4, and 8? That is 16. So a beautiful thing you can do to get rid of these annoying denominators is multiply everything, both sides of the equation, by that LCD, okay? Now, let's look at what that does, at least over here, okay? We'll start here. What that does is the 16 cancels with the 8, and the 16 turns into a 2, and the 8 turns into a 1. So really, we've just gotten rid of that denominator down there, didn't we? And then it's just going to be 93 times 2, which is 186. 186. And let's look at what happens over here. Well, clearly we have to distribute the 16 into everything, okay? We have to distribute the 16 here, and we have to distribute the 16 there. Now, when we distribute the 16 here, the 16 is going to cancel with this 16, leaving us only with, guess what, 33. That's it. Oh, we have to distribute the 16. We have to distribute the 16 to this x also. That's actually very important. So nonetheless, 16 times this first fraction gives us just a 33, which is amazing. And then we have 16 times x, which is just 16x. And then we have this 16 times 19 over 4. Well, let's think about what that is. 16 times 19 over 4. Well, this 16 is going to cancel with the 4. So the 4 is going to cancel out and turn into a 1. And this 16 is going to turn into a 4. So that's just going to be 4 times 19. And that is 76. So that is going to be 76. Just going to blow this up a little bit. All right, so I have an ugly equation here. It's kind of all weird looking, but you got the idea. So we have 33 plus 16x plus 76 equals 186. Do you see how we got rid of all the denominators? It's like, thank God. So I'm going to write it so that it's in this order, 16x. And when we combine the like terms of 33 and 76, we're going to get 109. So it's really 16x plus 109 equals 186. We're going to subtract 109 from both sides, and that gives us 77. And then we have 16x equals 77. And 77 divided by 16 is 4.8 something. Okay, in fact, it's 4.8125. Now, if you look at the answer choices, all of the answer choices are written in mixed numbers, right? So really, we should investigate, well, what does this equal as far as a mixed number? Well, it's safe to say the whole number is going to be 4. But then the question is, well, what about the fractional part? Well, let's go back to the previous step and just remember that what we did there was 77 divided by 16, right? And that's how we got our 4.8125, okay? Well, this is old school, just that strategy of turning an improper fraction back into a mixed number, in which case it would be 77 divided by 16. You just go old school long division with it. 16 times what gives you 77? Well, 16 times 4 gets us just underneath 77 without going over, and 16 times 4 is, well, that's going to be 40 plus 24, so that's going to be 64. And then you subtract the 64, which gives you a remainder of, let's see, 3 there and 1 there. So it's a remainder of 13. Totally a remainder of 13. Now, in case you guys at home forgot, the quotient is right there. And that always gives you the big number. The denominator is always going to be the divisor. So that's going to be 16. The denominator is always going to be the divisor. And the numerator is always going to be the remainder. So that's some old school stuff that many of you learned probably a while back. But yes, it is a return to that foundation. 4 and 13/16 is the answer, and that is answer choice D. So what they're asking in problem number 19 is, which of the following equations does not represent a line? Well, this is sort of more of a problem that requires you to just understand the different classifications of equations, okay? Bottom line is, if you have something, and this is just a made-up example right here, this is not from the problem, it's a made-up example. If you have an exponent of 1, and that is the degree of the equation, meaning the largest exponent represented in the equation, well, that is what we refer to as linear. If you have an exponent of 2, and therefore the degree, the largest exponent is 2, and therefore the degree of the equation is 2, the largest exponent is 2. This has an exponent of 1, but this is the larger exponent of 2. We call that quadratic. That's a quadratic equation. Now, there's other ways of classifying polynomials, okay? For example, you could also classify polynomials by how many terms they have, like it says 2 terms, and that's a binomial. But when you're focusing on the degree, meaning the largest exponent present within the equation or polynomial, this is the way to classify it. So an exponent of 1, a degree of 1 gives you linear, a degree of 2 gives you quadratic. If you had something like this, well, the degree here is clearly 3, and we call that cubic. And I'll just say that if the degree was 4, it would be quartic. If the degree was 5, it would be quintic. But the only one, and this goes on, we could keep going with these classifications, but the only one of these that would actually form a line would be the degree of 1, because that's linear. And you need to remember that linear means line. Means if you were to graph this equation on an xy coordinate plane, it would form a line. Whereas this one would form a parabola. This one would form some shape that looks like this. Okay, and by the way, parabola looks like that. Okay, and so on and so forth. Okay, so clearly we can see that answer choice E says x squared plus y equals 5, and that corresponds with a quadratic, and this one would form, therefore, a parabola, not a line. So answer choice E is the odd man out. Answer choice E is not a line, and therefore it's the answer, because that's what they asked for. Which one of these is not a line? So that's the answer. So for problem number 22, the final question is, which of the following is the maximum speed in miles per hour Damon can be driving? So the braking distance is less than or equal to 150 feet. Now think about the braking distance. That means the distance, like you hit the brakes really hard in the car, but then the car skids for a certain amount of distance. Now think about the physics of this. The faster you were going before you slammed on the brakes, the longer the skid is going to be, okay? The longer the braking distance is going to be. So it's good to sort of just see that, conceptually. The larger the speed, the bigger the braking distance. The larger the speed before you slam on the brakes, the bigger the braking distance. So it's good to just know that, because what they're saying is, what's the maximum speed Damon can be driving so the braking distance is less than or equal to 150 feet. So the maximum speed that we're looking for is the speed that would cause the braking distance to be at its maximum, which in this case is 150 feet. The maximum speed that we're looking for is the speed that would cause the braking distance to be 150 feet. So that means we could set the speed up to be 150 feet. Now I know it's an inequality, but really, since we're maximizing the speed, we want the maximum braking distance that's allowable given this, given the question. So the maximum braking distance is 150 feet. So we want to set that equal to 3 times x squared, which is the modeled expression representing, braking distance, all over 40. Okay, because once again, yeah, we want this to be less than or equal to 150, but we're looking for the maximum speed, which means we want to maximize this part and then just find out, okay, well, which x would correspond with a braking distance of 150. Now at this point, it's pretty easy actually. Well, it's easy if you feel confident, we could say, with your algebra skills. We want to solve for x. Well, the bottom line is it'd be nice to get this, binomial right here that has x squared and 10x in it. It'd be nice if we could just get this parentheses, by itself. And a good first step to doing that is to multiply everything by 40. Let's get rid of that denominator. Okay, we're going to multiply everything by 40, meaning both sides of the equation by 40. And in doing so, we cancel those 40s out. And then we end up with 150 times 40, which is 6,000. 6,000, and that equals what we have left over, which is that. Now I'm going to keep this in green parentheses just so we can see that that's the same as that. Now, I think pretty much everyone at home would know that what we need to do now is divide both sides by 3, okay? Or hopefully you know that. I mean, some of you might be wondering, could I have distributed the 3? Well, yeah, actually you could have distributed the 3, and that would have led to the right answer too, but I don't know. I kind of like the idea of getting the x's by themselves, right away. I mean, we have this opportunity to do that now. Why not? So 6,000 divided by 3 is 2,000. So that's going to be 2,000 equals x squared plus 10x. And then it's like, okay, well, what the heck do we do with that? Well, hopefully those of you at home realize this is a quadratic equation situation where we have an x squared, we have an x to the first power, and we have a constant. And in reality, there's 3 terms that we're contending with here. We've got this term here, we've got this term here, we've got a constant term. So hopefully some of you remember that it can be good to set this equal to 0. So we're going to subtract 2,000 from both sides. We're going to subtract 2,000 from both sides. And what do we end up with as a result? Well, clearly we end up with this turning into a 0. And then we're going to have x squared plus 10x minus 2,000. Minus 2,000. And at this point, we're going to factor. We're going to ask ourselves, what two numbers multiply to negative 2,000 but add to 10? What two numbers multiply to negative 2,000 but add to positive 10? So many of you might be racking your brain about that, and I don't blame you, because 2,000 has a lot of factors and it's annoying, right? But you know that the factors need to be close to each other because one of the factors has to be positive, another one has to be negative, and it's like when you combine them, you got to get 10. So there should only be a distance of 10 between them. So after some consideration, what you will soon see is that positive 50 times a negative 40 would give us a negative 2,000, and a positive 50 plus a negative 40 would give us a 10. So that is our ticket home when it comes to this factorization. Now, when we do the factoring of trinomials, quadratic trinomials, you're going to have these two parentheses. Many of you at home would quickly recognize that, at least in this case, it's going to be x and x. And then you're going to write those two magical factors in there. We're going to have a positive 50 and a negative 40, which really means that the answer to the problem, if we were to just be interested in simply the algebraic answer, it would be x equals negative 50 and positive 40. Now, since this is a problem dealing with a real-world situation where x represents a speed, and not only that, it represents the maximum speed that we could be, driving that would cause a braking distance of 150 feet. Well, the maximum speed is the larger of the two. It's the larger of the two, okay? And also it needs to be positive anyway because we're dealing with speed rather than velocity, okay? So we're dealing with speed. So we're looking at 40, and that is the answer. The answer is H. Okay, so for problem number 24, the final question is, how many different two-person combinations of one junior and one senior are possible? Now, this turns out to be a fundamental counting principle problem. Now, what I mean by that is, if you want to figure out how many two-person combinations of one junior and one senior, well, let's imagine that this underline represents the event. It's an event called the choosing a junior. And we're going to say this underline represents another event called choosing a senior. Now, the fundamental counting principle says that if you want to know how many possible combinations of choosing a junior and choosing a senior you can make, well, you just take a look at each underline and just ask yourself, well, how many possibilities are there? How many possible choices are there for this first underline? And in this case, when it comes to juniors, it's going to be 125 possibilities. And then you ask yourself, well, how many possibilities are there for choosing a senior? Well, according to the problem, there's 100 possibilities. Then what do is you multiply those possibilities times each other, and then you will get 12500, aka 12,500. That is a fundamental counting principle problem where I would advise any student make an underline representing the first event, make another underline representing the second event. Now, what do I mean by event? Well, in this context, the event is the choice of a junior. That's an event. And the second event is the choice of a senior. And then you ask yourself, well, what are how many possible things could happen in the first event? How many possible things could happen in the second event? And then you just multiply the possibilities across, and then you have your 12,500, which turns out to be K. So problem number 28, they start by saying for all x greater than 21, um, blah, 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 blah. Okay, there's this huge, ridiculous problem. In fact, I'll write it because I'm going to have to write it anyway. So they say for all x greater than 21, we have this scenario, and we want to know, what does it equal, by the way? This ridiculous scenario. X squared plus 4x minus 21. Now, it's often the case that when they say something like for x greater than 21, that could be their way of saying, like, don't worry, there's no value in x that would cause this whole thing to be undefined, okay? It's often the case that when they say things like that, that's their way of saying, like, proceed as normal, don't worry about it, this fraction is not undefined. Because some students might be like, well, what about, if x was this and x is that, then the whole thing would be undefined, right? And undefined is not one of the answer choices, so what's going on with that? So sometimes the test makers of either the ACT or the SAT, they make sure that they cover their butt by saying, don't worry, this thing is not undefined, proceed as normal, okay? Now the problem is with this problem is that a lot of students might be tempted to take some number like 22 or 30 and plug it into this thing and then find out what that equals. And you know what? That actually would work. But the problem with that is, who really wants to be squaring? Like, let's say you choose 22. Do you really feel like squaring 22 and then going through all these motions? Absolutely not. So what you should do is, at the very least, check and see if you can factor this and do some cancellations, okay? In fact, you see the answer choices, and you'll see that many of the answer choices feature sort of a reduced fractional expression. So that serves as a hint that, well, maybe you just see what happens if you simplify this thing. Just try simplifying it. Well, how do you simplify it? You do cancellations. You factor these larger ones and see if anything would cancel out. Now, the bottom line is, um, these can be factored upon closer inspection. Let's look at this top one, x squared plus 8x plus 7. What factors, or what two numbers multiply to 7 but add to 8? Well, that would be 7 and 1. So what I'm going to do is I'm going to wrap this one in red. I'm going to wrap this one in blue, okay? And we're going to leave these in black. So I like to color code things. So really what we have on the next line is a new situation. Okay, we'll do a little divider here, just in case. Okay, we're going to have a new situation, and underneath it's going to be blue, because I know that that can be factored too. I could just tell. And we're going to get to that in a second. So, as far as the top one, as far as these black ones, actually, we'll fill them in right now. This is the way I like to do things. Like, as soon as I know something's definitely going to be on the next line, just go ahead and write it. I don't care if it's out of order. It's like, okay, x minus 3, x plus 1. Just write it. I like to keep moving. When it comes to this one, what two numbers multiply to 7 but add to 8? Well, that's going to be 7 and 1. So we're going to write x plus 7 and x plus 1. Corresponding with the red, corresponding with the blue. What two numbers multiply to negative 21 but add to 4? Well, that would most definitely be positive 7 and negative 4, right? Positive 7 and negative 3 rather. X minus 3. Right. Okay, now many of you at home can probably see, well, we have cancellations all over the place. It's amazing. We got x minus x plus 7 canceling with that. I'll do it in yellow. We got x plus 1 canceling with that. We got x minus 3 canceling with that. Now, it's important to remember, when you cancel stuff, what happens? Well, it all turns into 1. Doesn't turn into 0. It turns into 1. So what you really have here is 1 times 1 times 1, and you have 1 times 1 times 1, and it's going to be 1 over 1, right? And that equals 1, which is answer choice F. Answer choice F, and that's how you do that one. So problem number 33 is deceptively simple. Um, First they say, oh, the length of the curve is longer than FG. Well, it's like, yeah, I mean, kind of makes sense, right? But that turns out to be extra information that you don't need. So they're just like distracting you with that. At the end of the day, the final question is about how many coordinate units long is FG? Well, the bottom line is, let's just like ignore the darn curve. And we're going to focus only on FG. So we got FG that goes like that, right? That's F, and that's G right there. And F is clearly at 200 units, and G is also at 200 units. Okay, 200 units. So this is a triangle that is such that two side lengths are 200 by 200. Now, there's another thing about this triangle is that that's 90 degrees. This is 90 degrees because it's the XY coordinate plane kind of thing. And that's 90 degrees. All right, it's a right angle. So what we have in our hands here is a right triangle where one of the legs is 200, another leg is 200, and now they're asking us for FG. Well, what is that? That's the hypotenuse, right? That is the hypotenuse. And if we could just find the length of that hypotenuse, well, we'd have the answer. Well, there's two ways of going about it. Number one, you could use the Pythagorean theorem. That's totally fine. If you want to use the Pythagorean theorem, that's fine. Okay, so we're going to do that right now. We're going to be like, okay, well, Pythagorean theorem is a squared plus b squared equals c squared, and that's going to be 200 squared plus 200 squared equals c squared, and that's going to be, let's see, 4 with 4 zeros, big number, plus the same thing, and that equals that, and then it's going to be like 8 with those zeros, 80,000, right? And it's going to be that, and then you would have to take the square root of both sides, and you would end up with the square root of that. I'll do a little comma for these as well. You would have the square root of 80,000, which would basically turn out to be around 283. All right, and I'll use these approximation symbols. Instead of writing equal, you could do the squiggly lines, which means that C is approximately 283. So that would work. Now, another way of going about it that is a little bit faster. There's a way of going about it that is a little bit faster that basically says there's a such thing as a 45, 45, 90 triangle. So a quick review of that. 45, 45, 90 triangle. That means that you have a 45 degrees, you have 45 degrees, okay, and you have your 90 degrees there. It's always going to be the case that whenever you're dealing with a 45, 45, 90 triangle, you will have a leg that is, maybe we'll call it A units long, another leg that's A units long, and the hypotenuse without fail will always be whatever that leg length is times radical 2. So once again, the hypotenuse, when it comes to a 45, 45, 90 triangle, will always be the case that the hypotenuse is always going to be whatever a leg length is, here it is, times radical 2. And in fact, just to sort of denote that, I'm going to wrap these in parentheses and just wrap this in parentheses because this is one of these guys, but it's one of those guys times radical 2. Okay? Notice something about 45, 45, 90 triangles. This is a right triangle for sure because it's 90 degrees there. But you know what? It's also an isosceles triangle, right? I mean, this side length right here is totally the same length as that side length right there. So not only is it a right triangle, but it's also an isosceles triangle. I have found that that is a helpful mental note to make, okay? Because what we're dealing with here is most definitely an isosceles right triangle. I mean, look at it, it's 200 and 200 right there. So guess what? That's going to be 200. That's going to be 200. In fact, I'll write it in blue. 200 times radical 2. Boom. for the exact same reason that that's a radical 2, well, this is going to be 200 radical 2. So just stare at these two situations until it clicks, if it hasn't already. And this is something you just plug right into your calculator, and that would give you something around 283, okay? So if you forget that, it's fine. You could always just simply rely on the Pythagorean theorem. In fact, that's one of the nice things about the Pythagorean theorem, is that it would pretty much work under any circumstance when it comes to these, you know, figuring out what a hypotenuse is and you have the legs or whatever. It would work, but the faster way is most definitely to would be a matter of remembering the 45, 45, 90 triangle situation, and then just realizing, oh, well, if that's 200, that's 200, this would be 200 times radical 2. So hopefully that makes sense. And that would give you the correct answer as well. And by the way, the answer is therefore, looks like it is D. So problem number 34 in a way demands that you really pay attention to what's happening with this diagram and what they're saying and all that. Because basically what they're saying is he finds the initial estimate A for the shaded area by using FG and computing 1/2 200 by 200. So it is that A equals 1/2 200 by 200. Now I'm just going to write the numbers here, okay? A equals 1/2 200 by 200. That is literally the area of the triangle, right? Isn't that the area of the triangle? 1/2, we could say base times height. I mean, that's the area of a triangle, where it so happens that this triangle is such that it has a base of 200, right? A base of 200 and a height of 200. So what Tran did is he found an initial estimate for the shaded region, and the shaded region is underneath the triangle. Underneath the triangle. He's trying to estimate that, right? All this stuff. He's trying to estimate. It's like, well, shaded region, the area of it's basically like the same size as the triangle, pretty much, right? It's pretty much the same size as the triangle. So I'm going to estimate it by just finding the area of the whole darn triangle, and I'll call that my estimate of the red shaded region. I'm going to find the area of the triangle, and I'll call that my estimate. So the area of the shaded region, however, clearly you can see it's not the same as the area of the triangle. It's clearly less than the area of the triangle, which is what he's using as an estimate. That's the crucial insight. That's all. You don't really have to calculate anything in this problem. You just have to realize, like, okay, Tran, good job, dude. You made an estimate for the shaded region, but, the estimate is going to be a little bit bigger than the shaded region, and therefore the shaded region is going to be a little bit less than your estimate, so therefore answer choice F is the answer. The area of the shaded region is less than 20,000 square units because the curve lies under FG, and FG is this thing. The curve is under FG, which makes this shaded region less than the area of the triangle. So the answer is F. Now, quickly, let's look at the other answers. Answer is G, less than 20,000 square units because the curve lies over FG. Well, now, here's FG, right? If the curve lied over FG, well, then we'd be dealing with, this whole shaded region right there. So it's like that. I would encourage you to go through the rest of the answer choices and find out how or why all of the other answer choices are just flat out wrong, okay? But answer choice F definitely works for sure. Moving on. So problem number 37 is one of those classic word problems where there's like so much going on that you might actually want to use a table. And especially when it comes to, there's all this stuff going on that's sort of related. So for example, there's two companies you're dealing with, each of which has a per mile cost, each of which has a per day cost. Okay, so from my point of view, that's where something like a two-way table would really come in handy. Okay, now the two-way table look something like that. Now, you're often going to want to sort of extend it too because there's going to be totals involved, which you're going to kind of see in a moment. Now, bottom line is this would be the Seahorse Company and the Ocean Blue Company, okay? And there is a cost associated with days, so it's going to be the total day cost. Total day cost. And there's also going to be a cost associated with miles traveled. So there's a total mile cost associated with using each company. And then over here is going to be the total cost per company, depending on which company you use. Now, we know according to the problem that we only have $255 to spend on each company. So actually, interestingly enough, we can fill out these cells right here in the table because we know that we only have 255 of total cost to spend on Seahorse if we choose Seahorse. We also know that we only have $255 to choose for the Ocean Blue should we choose the Ocean Blue, right? And what we're doing really is we're comparing these because the final question is which company, if either, allows them to travel more miles for the 2 days and how many miles more. So in a way, it's really two questions in one. But either way, we're going to figure out, well, how many more miles could we travel given our fixed total cost with the Seahorse? Uh, how many more miles or less miles could we travel with Ocean Blue given the fixed cost? Well, what is the fixed cost? The fixed cost is $255, right? That's the fixed cost that we have to spend on each. And what we're going to do is we're going to investigate, well, how many miles could we do given that fixed cost in Seahorse? How many miles could we do with Ocean Blue given this fixed cost? Well, let's take a look at the total day cost column here. For Seahorse, apparently it's $50 per day. But according to the problem, if you look at that last final question, we're traveling 2 days. So what is the total day cost for Seashore, or Seahorse rather? It would be $50 per day times 2 days, right? And what is that? Well, that is, of course, $100. So that's the total day cost for the Seahorse Company. And while we're at it, let's talk about the total day cost for the Ocean Blue Company. Well, according to the problem, the Ocean Blue car rental charges $60 per day, $60 per day times 2 days. And of course, that will be 120 total dollars. So that is the total day cost for the Ocean Blue Company, right? What about the total mile cost for the Seahorse Company? Well, we don't know how many miles. In fact, that's what we're kind of trying to figure out, actually, according to the final question of this word problem. We don't know the miles yet, but let's at least set this up so we're going about this in an organized fashion. The total mile cost for the Seahorse Company is 25 cents per mile, and we're just going to call that literally 0.25 times however many miles, which is X in this case, okay? Let's look at the total mile cost for the Ocean Blue Company. Well, according to the problem, it's 20 cents per mile, so that's going to be zero point 0.2. I'm not going to say 0.20, I'm just going to call it 0.2. 0.2 times however miles you're able to travel in the Ocean Blue Company. Well, I don't want to call that X. I'm going to want to assume that that's going to be a different number because it probably is a different number. And therefore I'm going to call it Y, okay? So in other words, X represents the amount of miles you're able to travel with the Seahorse Company if your fixed cost is 255, and Y represents the amount of miles you're able to travel with the Ocean Blue Company, assuming the fixed cost is 255. Now, what I'm actually going to do right now is something interesting. I'm going to get rid of this equal sign, even though it makes sense to put it within that cell, because I don't want to confuse the issue. Because the reality is that 100 plus this 0.25x should equal 255. Because isn't it true that the total day cost plus the total mile cost for each company, well, that should equal the total cost. So in fact, you know what I'm going to do? I'm going to get a little crazy and write a little plus symbol because the total day cost plus the total mile cost should equal the total cost in general. So I'm going to write an equal sign right there too, okay? Now, let's remember, therefore, that this cell, 100 plus 0.25x, equals 255. And we should also remember that 120 plus 0.2y should equal 255. So we've organized the information, and now we're able to very clearly see, well, what are the equations that we need to now set up? Well, one of the equations definitely has to do with the Seahorse Company, which basically says 100 plus 0.25x equals 255. That's one equation that we can most definitely use to figure out what x is, right? Because we want to figure out what is this mileage that you're able to do with the Seahorse Company. Well, that's x. Another equation we could set up is the one that has to do with the Ocean Blue. That basically says 120 plus 0.2y equals 255. So these are two equations that we could totally use to figure out the miles we're able to travel with the Seahorse Company and the miles we're able to travel with the Ocean Blue Company. And let's do each one separately and just compare x to y after that. So looking at this equation on the left, 100 plus 0.25x equals 255. Now, I'm a big fan of getting rid of decimals as soon as I see them. And the way that I'm going to do that is I'm going to multiply everything by 100, which would move this decimal place twice to the right. By multiplying literally everything by 100, all right, 100, we would be moving this decimal place twice to the right because this 100 would distribute there and there. And the moment the 100 would distribute there, we'd be moving this decimal place twice to the right, which is what I want. Now, 100 times 100, it's pretty easy. Anytime you multiply a number by 100, you just tack on 2 extra zeros. So this would become, on the next line, 10000, which is really 10,000. And this would become 25x. Notice how the decimal has been moved 2 places to the right, becomes 25x. And then we have 25500, aka 25,500. Then, of course, we would just subtract 10,000 from both sides, which would leave us on the left-hand side with 25x. And on the right-hand side, it would be 15500, aka 15,500, dividing both sides by 25 would give me 620. So x is 620. Now, in other words, the amount of miles you're able to drive, if you have a fixed amount of money to spend, right, fixed cost of 255, the amount of miles you're able to drive using the Seahorse Company would be 620 miles. Okay, so that's x. So now, of course, we're on a mission to find y, which pertains to the amount of miles that you would be able to drive with the Ocean Blue Company with a fixed cost of $255. Similarly, I'm going to multiply both sides of the equation by a number in order to get rid of the decimal. Now, in this case, however, I only need to move the decimal over once to the right. So what I'm going to do there is multiply both sides by 10 because that would do the trick. Okay, I'm going to write times 10 times 10. Okay, so as a result of that, we would be tacking on only 1 0 to 120. So 120 becomes 1200, aka 1,200. And then over here it would be 2y. And over here would be 2550, aka 2,550. Subtracting 1,200 from both sides would then give us 1350, also known as 1,350. And dividing both sides by 2 would then give us 675. Now, the first thing you need to make a mental note of, at least as it pertains to this problem, is that 675 is more than 620. So the amount of miles that you'd be able to travel with the Ocean Blue Company, assuming you only have $255 at your disposal, you'd be able to travel more miles with Ocean Blue. That's actually the first sort of question they ask. Which company, if either, allows him to travel more miles? Well, that would be Ocean Blue. So already B and C are contenders. Answer choice B and C are contenders. But then the other part of the question is, how many miles more? Well, that's easy. 675 minus 620. Well, that's going to be 55 extra miles, 55 more miles, right? That is why answer choice B is correct. Answer choice B says Ocean Blue, comma, 55. Now that took me a pretty long time to explain. I don't want you guys at home to freak out because just because it takes me long to explain it doesn't mean it's going to take that long to do it. Okay? Obviously, with practice, you'll sort of know what to do. Some of you might not even need the table. Some of you might have been able to just set up the equations right away, and if that's the case, it's fine. But setting up a table is a good way to just keep all the information organized, to see how everything relates to everything else, and sort of take it from there. So it's at least something to consider. So for problem number 38, all you really need to do is remember that the area of any parallelogram is simply base times height. Okay, so very quickly, if you had a parallelogram, well, this entire side would be the base, but you do have to be careful when it comes to the height. The height is, you can think of it as almost like the altitude. It's the, you know, distance from the top to the base in such a way that would form 90 degrees with the base. Okay, so that's the height. Okay, so that's the height. So yeah, when it comes to this problem, you just need to calculate the base and calculate the height, and of course you have to be somewhat savvy in that you have to pay attention to the XY coordinate plane. And upon inspection, you would indeed see that the base is 10, right? I mean, you can kind of see that, right? Due to the fact that that is 10 comma 0 right there. And then the height, you'd have to ask yourself, okay, well, I don't know, how much distance is there from the bottom to the top? How much distance is there from the bottom to the top? Well, that's given by this point here, which we know is 3, 6. So we have 3, 6 right there. And that therefore means that it's 6 units up, so the height is 6. So we're looking at 60. And how did I get 60? Well, again, you just multiply it, base times height. 10 times 6 is 60. And thank God, because really, who wants to deal with all those radicals? So the answer to that one is G. G. Problem number 39 is a nightmare problem for any student who fell asleep during that one class where the teacher went over the definition of natural numbers, integers, rational numbers, real numbers, and complex numbers, okay? Yeah, and honestly, obviously, these kinds of concepts are sort of easy to forget as well. So I'm going to break it down for you. First of all numbers that you can conceive of at least up to this point are complex numbers. Let's just leave it at that. Okay. I'm going to break this into two different factions, though. We're going to call this one the imaginary numbers. Okay. And these are the numbers that feature the number I, which is really like an interesting concept. And that equals this, all right, the square root of -1, okay? And that's something that, elsewhere on the ACT, other problems feature, sort of loose understanding of what that means. But the other kind of complex number, if it's not imaginary, then what it means is you are most definitely dealing with a real number. Now, a real number is any number that could be on a number line, including the numbers in between the tick marks. So for example, 1/2 is a real number because it's on the number line somewhere. If you can close your eyes and point to a number line, and point to some number, that number is what we call a real number. Okay, so that's good to know. Okay, now that further splits into something called rational, and irrational. Okay, rational and irrational. Now, rational numbers are numbers that could be represented as A over B, where A and B are integers. Now, integers is usually represented by the Z. Now, an integer is a whole number, positive or negative. Whole number, positive or negative. So therefore, the rational number, something like 3 over 11. Well, that's rational. You know what else is rational? 15 over 2. That's rational because 15 is an integer, a whole number, and 2 is a whole number, right? And what else is rational? Something like 10 is rational. Well, why is 10 rational? Well, 10 is rational because secretly there's a denominator of 1 underneath that 10. So we know that literally all whole numbers like 10 also happen to be rational numbers. Okay, so A and B are part of the set of integers. So the numerator and the denominator are integers. And it ends up being either nice looking fractions like this or even whole numbers. It's also the case that if you were to turn any one of these rational numbers into a decimal, like for example, 3 over 11, that could be turned into a decimal. All you have to do is hop into your calculator and divide 3 by 11, and then all of a sudden you'd have a decimal. So if it was to turn into a decimal, let's take 15 over 2. Well, that's 7.5. So if you were to take any of these numbers and turn it into a decimal, it would result in a situation where you'd have a repetitive pattern that goes on forever. Goes on forever and it repeats. Now, in the case of 7.5, you have repeating zeros that go on forever. So that right there is a repetitive pattern that goes on forever, even if it's just zeros. Okay? Now, if it's not a repetitive pattern of zeros, well, then it would be like 7.56565656 forever. But that 5, 6 would be a repetitive pattern that goes on forever. And as long as you have a repetitive decimal pattern that goes on forever, it's rational. Now that begs the question, well, what the heck is irrational? Well, irrational are things like pi, things like the square root of 2, things like the square root of 3, things like the square root of 5. Okay? These are classic examples of irrational numbers because the bottom line is you cannot represent these as a fraction of some whole number over another whole number. It's impossible, and there are proofs beyond the scope of this sort of lesson that would help you understand that, okay? That would prove to you that it's impossible to represent these as A over B if A is a whole number and B is a whole number. And furthermore, anytime you convert one of these into a decimal version, it does not give a pattern that repeats forever. Okay, so for example, pi, we call it 3.14, but the bottom line is there's all these numbers that go on forever and they do not repeat a pattern. In fact, they have contests where they challenge mathematicians to memorize, pi to the whatever decimal. Right? And why is that a difficult challenge? It's a difficult challenge because these numbers never repeat. That's why it's hard. I mean, it'd be easy to memorize something like this. It's like 7.50 forever. I'm done. I just memorized it, right? Whereas this thing, the pattern doesn't even repeat. So it's crazy. Same thing with radical 2, same thing with radical 3, same thing with radical 5. If you were to plug that into your calculator, you would see a whole bunch of numbers, decimals, that do not repeat at all. Okay, so that's that one. Now, when it comes to rational numbers, which I will now sort of, I think I'm going to circle it actually because this all is the same thing. Okay, and really this is all one group of numbers. We'll call this a group of numbers. So once again, complex real, which splits apart into rational or irrational. Okay, and then when it comes to rational numbers, well, that's either, I'll just say integers or non-integers. Okay, integers or non-integers. Okay, now the integers, what do we mean by integers? Integers are, we can say whole numbers, whole numbers. And what does that look like on a number line? Well, what that looks like on a number line is literally any of the tick marks on a number line, okay? Any of these tick marks on the number line, notice how 0 is included. So 0, yes, 0 is an integer, okay? 0 is an integer. It's the only integer, by the way, that's neither positive nor negative. Every other integer is either positive, because you either have positive tick marks forever to the right on the number line, or you have negative tick marks forever to the left on the number line. But the only integer that is neither positive nor negative is 0, so that's kind of interesting. All right. Now, what are non-integers? Well, we call those fractions. Okay, fractions. Fractions could be represented as decimals as well, right? So that is a quick overview of the way that rational numbers can be split. They can be split into either integers or non-integers, okay? Might as well draw a box around imaginary as well. So it started with complex, which breaks into real and imaginary. We kind of left this one alone because imaginary is just imaginary. Just leave that alone for now. We got real, which could be split into two. We got rational, which could be split into two. Okay. Non-integers are fractions. I'll write that in quotes as well. Okay, fractions. So then we have integers. Well, it's like, what could you break that up into? And this is kind of subjective, but we're going to break it into, we'll call it natural numbers, natural and non-natural. Okay, so the natural numbers are 1, 2, 3, 4, 5. And we'll say non-natural integers. Okay, we'll call it non-natural integers. Okay, so the natural numbers are all of the numbers that you would actually find like in the real world that you could see with your eyeballs. Okay, like no one has ever actually seen 0 apples, but we've seen 1 apple, we've seen 2 apples, we've seen 3 apples, right? So all the numbers of things that you could actually see with your senses, well, that pertains to natural numbers. Okay, that's one way of thinking about it, at least. And then the non-natural integers, we'll stick with the word integers there, are all the other integers like 0 and the negatives. You know what I mean? So that's that one. Okay. Before we go back to the problem, we need to remember that because of this relationship where like complex is at the top, that could be split into 2 different things. Real could be split into 2 different things. Rational could be split into 2 different things, and so on. It therefore logically stands that a natural number is a kind of integer, and an integer is a kind of rational number. A rational number is a kind of real number, and a real number is a kind of complex number. So in other words, a natural number, since it's a kind of integer, a natural number could also be considered to be a kind of rational number, right? A natural number could also be considered a kind of real number, and a natural number could also be considered a kind of complex number. It's just a special kind of complex number. It's the kind of complex number where it's 1, 2, 3, 4, and 5, right? 1, 2, 3, 4, and 5, I mean, that's all a kind of complex number. Okay, so hopefully that makes sense. You can see it's kind of like a tree of logic where it's like, since if a real number is a kind of complex number, well, and a rational number is a kind of real number, well, therefore, by the transitive property, a rational number is a kind of complex number, and that applies all the way down the chain. So that helps to know for problem number 39. So with problem number 39, they say n and m belong to natural numbers, which means that n and m is one of these guys. And then they're like, okay, which of the following sets, don't be thrown off by the word set. Set just means a group of numbers, a list of numbers, maybe with a particular property. It's just a group of numbers. So which of the following sets must n plus m belong? Well, if you add, 2 plus 4, 2 plus 5, or whatever, aren't you just going to get another natural number? I mean, you're not going to get a negative number, right? Because, for example, let's take 1. I mean, what other natural number could you possibly add to 1 that would ever cause you to get a negative number? There isn't any natural number that would ever cause you to get a negative number. So in that way, the natural numbers, there's a fancy concept called closed under addition. Natural numbers are closed under addition, meaning that anytime you add two natural numbers together, you're always just going to get another natural number. You kind of see that logically, conceptually. So n plus m is going to be yet another natural number. So n plus m belongs to the set of natural numbers. So n plus m is going to be found here. It's going to be found in here. Now, let's look at the thing. It's like the problem says, to which of the following sets must n plus m belong? Well, it belongs to the natural numbers. So that satisfies Roman numeral 1. Roman numeral 2 says it belongs to the set of integers. Well, yeah, because the natural numbers is a part of a set of integers. So Roman numeral 2 corresponds. Roman numeral 3, n plus m, does that also belong to the set of rational numbers? Absolutely. Natural numbers are a part of rational numbers. They're a special kind of rational numbers. Roman numeral 4, does the natural number, does n plus m, which is a natural number, does that belong to the real numbers all the way up here? Well, absolutely. Natural numbers are a kind of real number. And Roman numeral 5, do natural numbers, does n plus m belong to the real numbers, or the complex numbers rather? Well, yeah. According to this chart, we can very clearly see that the natural numbers, of which n plus m is a member, the natural numbers are a member of the complex numbers. So therefore, answer choice E is the answer, because n plus m literally belongs to all of those sets. It's just a special kind of integer. It's a special kind of rational number. It's a special kind of real number, and it's a special kind of complex number, but it is most definitely in the set of all of those. Okay, so that is problem number 39. Problem 41 is sort of a rare problem that features the statistics concept of expected value. And let me just say, the expected value is always the probability of one thing happening plus the probability of another thing happening plus the probability of another thing happening. Okay? So it's kind of like that, where you add everything up, you add all those products up together. Now, in this case, we have the following table, where this column has to do with the occupancy rate, and this column has to do with the probability. And the final question is, to the nearest whole number, what is the expected number of rooms that will be occupied on any day during the coming summer season? Now, we also are going to keep in mind that we have 80 total rooms, okay? 80 total rooms. Now, to find the expected value, it's actually kind of easy. All you have to do is multiply this times this, plus this times this, plus this times this, plus this times this, and that's going to give you a crucial piece of information. Now I'm kind of big on parentheses, so I'm just going to write all these first because I know that that's going to give me my sort of expected rate, we could say. So in the first parentheses, it's going to be 0.6 times 0.2. And this one is 0.7 times 0.4. I'm just going to write to the 10th place. I'm going to have 0.8 times 0.3. I'm going to have 0.9 times 0.1. And if I was to multiply that, I would have 0.12 plus 0.28 plus 0.24 plus 0.09. And that would equal 0.73. Now, that is the expected rate when you take into account the occupancy rate and the probability of actually getting the room. So that's the expected rate that we then multiply times the total number. So at the end of the day, we're looking at 80 times 0.73. And that turns out to be 58.4, which is approximately 58, which corresponds with answer choice C. Problem number 45 is a classic unit conversion problem. The final question is, at this rate, which of the following expression gives the number of gallons of fertilizer that Shima will mix in water for 0.5 acres of soil? So I think we can agree that if we could find out the unit rate of the number of gallons of fertilizer Shima will mix for 1 acre of soil, well, then we could just divide that in half in order to find out the number of gallons of fertilizer Shima will mix for 0.5 acres of soil. Okay, so I'm actually going to write that to make it very clear because it's always good to start with the big picture. So once again, if we could figure out the number of gallons Shima will mix in water for 1 acre, looking at acres of soil, if we wanted to find out the number of gallons Shima will mix in water for a half of an acre of soil, well, all we'd have to do is multiply whatever this number is in half. Now, to do that, it's really the same thing as multiplying times, 0.5. So if we could just find the number of gallons of fertilizer she'll mix for 1 acre of soil, if you want to figure out how many gallons correspond with a half of an acre of soil, well, you just multiply that number of gallons by 0.5 and take that half that amount, and then you'll have your answer. So in a way, this is the answer. But we need to find out the number of gallons of fertilizer Shima will mix in water for 1 acre of soil. And how will we do that? Well, we're going to do that. I'm going to set that aside. We're going to do that by doing a unit conversion. Now, a unit conversion often involves just drawing a nice little table and filling in the information that they gave you. And it's going to be a multiplication process and a cancellation process. But first, we need to fill up this table with the various relationships that were presented to us in the problem. Now, the first relationship they present is that 1 fluid ounce fluid ounce, that's the number 1, corresponds with 40 square feet. Now, at the end of the day, we're looking for gallons, which we could, call G, and we're looking for acres, which we could call A. Now, I don't see any G's or A's here, and in fact, we don't want the word fluid ounce or the word square feet to be in the final analysis. So we need to find a way to cancel, not so much the numbers, but the words themselves need to cancel, and they need to be replaced by the word gallon, we'll call that G, and the word acre. So the way to do that is to realize, okay, well, let's start with canceling out the word ounce. Not necessarily the number, but the word, we'll say fluid ounce, right? The phrase fluid ounces. We want to cancel that out. So what I'm going to do is I'm going to put that down here, because I know that if I put it down here, it's going to cancel, because this will cancel with that because of this cross cancellation. So the question is, did the word problem mention any relationship between fluid ounces and something else? Well, yes, apparently there's 128 fluid ounces corresponding with 1 gallon. So there you go. We have the fluid ounce phrase going to cancel out with this fluid ounce phrase. And we also introduced a new word called gallons, which is something that we want in the final analysis. We want gallons to be represented somewhere in the final analysis. But we still have this phrase square feet to deal with, which we're going to have to cancel that. So let's just ensure that we just put the word square feet up here, because if we do, that will ensure that this phrase is, word or phrase is going to cancel with this word or phrase. Was there a relationship in the word problem mentioning square feet with something else? Well, yes. Apparently, according to the problem, there's 43,560 square feet corresponding with 1 acre. I'm going to use the A for acre. Okay? And this is great because we put the word square feet here, which will cancel out with this word square feet. And we also introduced the concept of acres, which is something we want in the final analysis. So now what we do is the fun part. A lot of people like this part. You just cancel. Let's get a different color here. We're going to do purple. We just cancel the words, not the numbers, but the words that you want to cancel. We also have fluid ounce. We want that to cancel, don't we? And then what we do is we multiply straight across with the numbers and retain any of the words that are left over. So it's going to be 1 times 43560. So we've got our 43560. There was also the word gallons left over, so we want that, gallons. And down here we have 40 times 128, so that's going to be a fraction. It's going to be 40 times 128. And we also have the word A for acre. Now, you could think of this as one big fraction, but it's going to be helpful actually to think of it rather as sort of 2 separate fractions, where it's 43560. It's like this whole number, which I'll denote in a purple brackets. Whatever this number is, if we want to know the number of gallons of fertilizer Shimo will mix in water for 1 acre of soil, well, it's this many gallons. This whole number represents the gallons per 1 acre. So I'll say that again. It's this whole number that is the gallons per 1 acre. Okay? It's important to realize that. This is the amount of gallons per acre. So if we want to do, figure out how many gallons per half acre, like I said in the beginning, we need to do 0.5 times this number. So this purple brackets corresponds with this number. In fact, I'll make this purple brackets too. We're going to make this purple brackets too. This is the number we were looking for. This is the number of gallons of fertilizer Shima will mix in water for 1 acre of soil. This is the number of gallons per acre. So if we want to find the answer, we have to go 0.5 times this number. Now let's pause for a second. 0.5, secretly, could be represented as a fraction with a 1 in the denominator, where it's 0.5 over 1 times this, because anything secretly has a 1 in the denominator, any number. So the final answer is yes, it's going to be, this ridiculous looking number, 43560. Now, just to avoid driving some of you guys crazy, we'll put the comma there. It's 43,560. And then we have 40 times 128. Now, again, we got to do the 0.5. So it's going to be 0.5 over 1. Now, at the end of the day, we can kind of ignore that 1, right? Because 1 times this is just this. So really, at the end of the day, the final answer could be rewritten as 0.5 times 43560 all over 40 times 128. And that corresponds with answer choice C. Now, that was a very long-winded way of explaining that problem. I'd like to remind you that just because it took me that long to explain it does not mean that's how long it's going to take you to do it. In fact, with each of these problems, you're going to want to take hopefully around 60 seconds or less. Once you're familiar with how to do this stuff, I think you could do this in 60 seconds or less because you're not going to be teaching it like I'm doing. You're just going to be doing it, right? I think it's important to realize that, yes, it's a unit conversion. You do need to be fairly well practiced at unit conversion in general. And you also have to recognize that the final answer is going to be, it's going to be the number of gallons of fertilizer for 1 acre of soil, but it's going to be that times 0.5, right? Because we're looking at the number of gallons that correspond with 0.5 acres. So that's going to be half the amount of gallons. That would correspond with 1 acre. Okay? So that's how you do problem number 45. Okay, so problem number 48 certainly requires knowledge of trigonometry. So let's just get this out of the way. We definitely want to remember SOHCAHTOA. And for many of you at home, you're familiar with that. This is, for those of you not familiar with it, this is an easily memorizable word that helps students remember what the sine of an angle is, what the cosine of an angle is, and what the tangent of an angle is. And it's the case that this S represents sine, C represents cosine, and T represents tangent. And what this first part of the word is saying is that the sine of an angle equals opposite over hypotenuse, and the cosine of an angle equals adjacent over hypotenuse, and the tangent of an angle equals opposite over adjacent. Now, another thing you need to remember if you're dealing with trigonometry problems that feature the XY coordinate plane is, first of all angles, if you're analyzing various angles, all angles begin from this sort of starting line, and then you go open from there counterclockwise. So if I want to analyze an angle of 90 degrees, I'm going to start here and I'm going to open to 90 degrees. If I want to analyze an angle of 180, well, I'm going to start here, I'm going to go all the way over here. All right, and 360 would be a full revolution and so on, okay? Now, occasionally you're going to have to analyze the sine, cosine, and tangent of angles that open up from here. And that's where these four triangles really help, okay? I like to think of it as a bow tie. In fact, I think that it's smart to consider the bow tie. And the truth of the matter is this is just four triangles that are going to help you when you discover, what your cosine, sine, or tangent of any given angle is, because basically you start here, you open, and you're going to land in one of these quadrants, and depending on which quadrant you land in, you need to ask yourself, okay, which one of these triangles am I going to be dealing with? All right, now, without a concrete example, that might be annoyingly vague, so what I'm going to do is just dive right into this problem. According to the problem, we have an angle theta that opens all the way up and around, and it lands here. So we are going to be dealing with a triangle that is in the fourth quadrant. So it goes all the way around and it lands there, and we call that angle theta. Now don't be thrown off by that Greek letter theta. It's really just a variable that mathematicians like to use to symbolize an angle measure that we just don't really know yet. Numerically, it's very similar to x in algebra problems, only it's like x for angles, essentially, angle measures. So according to the problem, we open, a huge angle, and then we land somewhere in the fourth quadrant, and that's going to correspond with this triangle right here. Okay, so we have this triangle right here. They also give us some information that says, oh, by the way, this point right here is 4, -3. Now, what does that tell us? That tells us that with regards to this triangle that I just shaded, we go 4 units over and 3 units down. One way or the other, it's this triangle of all 4 triangles in the bow tie. It's this triangle that is sort of the MVP of this problem, because we opened all the way up and went here. Okay, so that's something to take into account. And from here, what I'm going to do is I'm going to analyze this MVP triangle separately, because that's going to be really helpful. Okay, so we're going to blow it up a little bit and we're going to analyze it. Now, we already know that the leg length over here is most definitely 4 units. And we also know that this is -3 units. It's 3 units downward, as it were. Okay, and then there's a hypotenuse that we don't quite know yet. And also, I will shade it because I want to make it look like the original triangle. So we're going to shade it. So make no mistake about it. All I did was take this triangle and kind of blow it up so that we could analyze it a little bit more closely and really see what's happening here. Okay. Now, when they ask for the cosine of this huge angle, all you have to do is take a look at the triangle that corresponds with that big angle, right? Find the triangle that corresponds with it, and then analyze that triangle. Now, the angle within the triangle that we're going to be focusing on is this one right here. It's this angle right here. So to be clear, whenever you're analyzing any of these triangles, you're always going to be focusing on the angle here, the angle here, the angle here, the angle here. So in other words, maybe they start by giving you some big whopping angle that lands somewhere. Then you take a look at what triangle it corresponds with, and then you focus on this little angle in here that's close to the origin. Okay? So these are things that are important to understand when you're tackling trigonometry problems. Okay, so we would have our answer if we could just find the cosine of this angle, actually. That's the beauty of this method, is that, yeah, it's like the cosine of theta, but really what you could do is analyze the MVP triangle and do the cosine of this angle here. Okay, so the cosine of this angle is definitely going to be adjacent over hypotenuse, right? Because cosine, which is mentioned here with the CAH is adjacent over hypotenuse. Remember, this has to do with sine, this has to do with tangent. So we're focusing on this one. So we are looking for the adjacent over the hypotenuse, and then we're done. That's going to give us the answer. Well, we have the adjacent to this angle. It's 4. It's the adjacent side is the side that's right next door to the angle. We already have that, so it's 4. And it's a positive 4. Notice how it's a positive 4 because it goes positively horizontally to the right. If it was over here in one of these triangles, the adjacent would be negative, right? But in this triangle down here, the adjacent goes positively to the right direction, as denoted by this positive x coordinate of 4 from this point right here. But notice how we need the hypotenuse here. We need this hypotenuse, and we don't have that yet, but the good news is we could use the Pythagorean theorem, or we could realize that this is a 3, 4, 5 triangle. Okay, this is a 3, 4, 5 triangle. Now let's use the Pythagorean theorem just in case some of y'all are not familiar with the 3, 4, 5 triangle. Pythagorean theorem says that one leg squared plus the other leg squared equals the hypotenuse squared. Well, in this case, we have something squared plus something else squared equals the hypotenuse squared. And the first leg is, we'll just call it 4. It doesn't really matter. This one would be -3. And then we would end up with 16 plus 9 equals c squared. And that's 25 equals c squared. And therefore 5 equals c. Okay. Now, you could, take the square root of both sides and say, oh, it should be plus minus 5. But it's important that you realize that the hypotenuse in these trigonometry problems, that's very important, the hypotenuse will always be positive. So the adjacent side might be positive or the adjacent side might be negative. The so-called opposite side of this red angle might be positive, the opposite side might be negative, but the hypotenuse is always positive. Remembering that the hypotenuse will always be positive could really save you a lot of confusion. So it's not plus minus 5, it's just the positive 5. C equals positive 5 here, okay? So this is 5. All right, so that's 5. And therefore, 5 is down here as well, okay? And that's the answer. That's the answer to problem number 48. Quick recap, they open theta all the way around. We figured out that the triangle that corresponds with our situation is this triangle in the bow tie. It's this triangle. We knew that this triangle had an adjacent side of 4 and an opposite side of -3. They were asking about the cosine, so we knew that we had to look at this reference angle right here, this reference angle right here. We had to analyze the triangle. We had to remember that cosine is adjacent over hypotenuse. And then we just went through the motions. We're like, okay, well, what's the adjacent? It's 4, positive 4. What's the hypotenuse? Well, okay, Pythagorean theorem, blah, 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 blah. And then we have 5. So clearly the answer is 4 over 5. And that's how you do problem number 48. So for problem number 50, the final question is, which of the following statements is not justifiable from the given information? So this is a question where you're going to want to really just investigate each answer choice and take it from there, okay? Now, let me just sort of recreate this real quick. A, B, C, F, D, and E. Okay, and we know that that's a 90-degree angle. Okay, so let's investigate each answer choice one at a time. According to F, AB, which is this right here, is parallel to EF. Well, that's definitely true because it is the case that if you have two segments or lines, in this case, the green lines, let's just say, okay? If you have two green segments or lines that are both perpendicular to the same third segment that's in between them, then the green lines or segments will be parallel. Okay, so that's important to understand. So that is worth memorizing for sure. It is somewhat intuitive, but that is an actual theorem. Okay, so that's that one. Looking at answer choice G, DE is perpendicular to BE. So let's take a look at that. DE is perpendicular to BE. Well, absolutely, because there's this 90-degree angle here, right? So this DE is totally perpendicular to BE. So answer choice G is true. Angle ACB, which is right here, is congruent to FCE. FCE. Yes, because of vertical angles, so these angles are across from each other, which makes them vertical angles, which makes them congruent, which makes them of equal measure. Answer choice J, BAC is similar to EFC. Let's see. BAC is similar to EFC. Well, the answer is yes, and here's why. Because if you look at these two triangles here, they share this angle right here in common. So they share a 90-degree angle, and there's a 90-degree angle in this green triangle as well, because this right angle is across from this right angle. That forms a linear pair, which makes angle CFE also a right angle. So that's an important insight you need. Okay, so definitely need that insight. So so far the green and blue triangles both share right or have a right angle, right? And then we also know from a previous investigation that angle BCA right here is congruent to angle ECF due to vertical angles. And therefore, it must follow that angle B is congruent to angle, we can call it FEC, this angle right there. Keep in mind, not the whole right angle here, but just this part only. That angle that I just gave a quadruple rainbow to, I'm going to give a quadruple rainbow to this one, is congruent with this angle. And the reason is because if the right angle plus the double rainbow plus this equal 180, well then this right angle plus the double rainbow plus whatever this is must equal 180, and therefore it follows that the quadruple rainbows angles are equal to each other. Now, anytime you have two triangles where the angles are equal to each other, where they both triangles feature the same angles, those triangles are similar. Okay, they're not necessarily congruent, but they're similar. Okay, now similar means same shape certainly, although not necessarily the same size. So these might be similar so long as one angle is equal to the other, this angle is equal to that one, and this angle is equal to that one. So that's one of the properties that lets you know two triangles are similar. So that leaves answer choice K, due to process of elimination, as the answer to this problem. Now let's look at it anyway. CE is congruent to ED. CE is congruent to ED. So answer choice K is suggesting that these two are congruent. And the truth is, there's really no reason to believe that, because you could conceive of this situation. Because this is a triangle that looks kind of like this big triangle here, but you can see clearly this side length is not the same as this side length. So you don't want to just trust your eyes always to know whether or not ED is congruent to EC or CE is congruent to ED. You don't want to always just trust your eyes, because the bottom line is something like this might be subtly happening up here, but you just can't see it with your eyes. Where, yeah, there's a 90-degree up here, there's a 90-degree down here, but these side lengths are not equal to each other. So that's problem number 50. Okay, so problem number 51 is a deceptively easy perimeter problem. I'm going to give you the labels according to what they said. Okay. Now, bottom line is, let's color code things such that everything that represents like a horizontal line has red, and everything that has a vertical segment or line has a green. And let's just take a look right now that if you were to sort of divide this up into like its component parts, isn't it true that this part would be 2? And isn't it true that this part would be 1? Because think about it, 1 is directly across from this one, it's color-coded green. 2 is directly across from this 2, it's color-coded green. So therefore, we just successfully found this entire side length, okay? Now, isn't it true, I'm actually going to erase this 4 down here. We're going to bring it down because we want to make clear that we are certain that the whole side length is 4. So isn't it true that this piece right here, though, is 3? And what would that make this piece? Some of you at home can already tell that would be 1 because 3 plus this 1 must equal 4, which is the whole thing. Now, if that piece is 1, well, doesn't that make this thing 1? It does. So at this point, we have enough information to find the perimeter. Now, what I'm going to do is just get rid of some of these numbers because we don't really need these little numbers here because we already have the whole side length. When you're interested in the perimeter, all you want is the whole side length. So the perimeter is going to be 3 plus 4 plus 1 plus 1 plus 2 plus 3. So it's going to be 3 plus 4 plus 1 plus 1 plus 2 plus 3. And if you were to add all that up, that would end up being 14, which is answer choice B. Now, let's get fancy, okay? And what I mean by getting fancy is we just went about that in a very intelligent way, if I do say so myself. But let's be very clear. Since the red of the horizontal segment here ends up equaling the total red horizontal segments up here, and since the green vertical segments all add up to these green vertical segments, the moment you found this whole green segment of 3, and the moment you found this whole green segment of 4, means that the perimeter will be 2 times 3, because it's this green segment, which is 3, plus this green stuff, which is 3. So it's going to be 2 times 3 plus 2 times 4 for the exact same reason, because this whole red is 4, and this red plus this red reflects this situation down below, which is 4. So if you ever get one of these 90-degree shape patterns where it's all 90 degrees like that and boxy looking, just know the moment you find one whole side length, that will be reflected on the other side. The moment you find a whole base or ceiling, that will be reflected on the other side. And this also would have given you 14. Food for thought. So problem number 52 is a very unique problem, and that's probably why most students, or many students, have trouble with it. So let's be very clear. The area of any triangle is 1/2 base times height. Okay, now it's also the case that the textbook where you learned that from probably presented a triangle with a base on the bottom and the height right here, you know, the sort of altitude that would form 90 degrees with the base. That's the height right there. But it's important to also remember that the triangle could be sort of turned around so that it looks like this. And maybe the height might be represented as this yellow line here, right? And the base would be the side length right here. So it's conceivable that you could do that, and it wouldn't change the area. It wouldn't even change the area formula. I mean, you could still do 1/2 base times height, And then you'd have the area of this triangle, okay? So it's good to be mentally flexible when it comes to this base and height situation. Now, as far as the problem itself, they give us the XY coordinate plane, of course. They have B, they have C, and they have A over here. And they also give us points. So the coordinates for B are apparently 0, 6. The coordinates for A are 8, 2. And the coordinates for C are, let's see, negative 3, 2. And we have a triangle. Final question is, what is the slope of that line? So apparently point C, which is this one, could be moved along a certain line with points A and B remaining stationary, and the area of ABC will not change. What is the slope of that line? So we're going to keep B and A in place. In fact, I'm going to mark them with red, which will communicate to us that these points are not moving. They're kind of stopped there, like a red light. They're stopped there. But this point C is flexible, and apparently there's a line that we could take it through. We don't really know which direction, but there's a line that we could take it through such that no matter where on the line C ends up, the area of this green triangle won't change. That's what they're saying. So the fundamental insight you need to know is that we could, if we wanted to, think of this side as the base. Okay, this side is the base, and the height is the distance from this base, which by the way could be extended here. The height is the distance from C, point C, to that base in such a way that would form 90 degrees. Now imagine if we just kind of moved C in this direction, only in such a way that this yellow distance between point C and the base stayed the same. So you can imagine maybe moving C here with this 90-degree base, and then C would end up being right there. And in that case, the triangle would be like that. But if you notice, if you move C from here to there, the base length is going to be the same and the height is going to be the same. So when it comes to the formula for area, and if you were to calculate the area of the green triangle, it would stay the same because the base is the same length and the height's the same length. So it's just base times height times 1/2. It's the same area. So the base doesn't change and the height doesn't even change. And imagine you brought point C, maybe even over here or something, right? Imagine that. And therefore, the height would still be this perpendicular line to the black base there. And now the triangle is here. Well, the triangle might look different, but the yellow height is the same and the black base is the same. So you could imagine moving C along this line in such a way that would keep the yellow height the same no matter what. And that line would be a track upon which C could move, point C could move, and would help retain the area of whatever the triangle ends up transforming into. So the triangle transforms over and over to a different looking triangle, but the area stays the same. So the question is, what is this track? What is this track? Well, you can see that this track right here is parallel to this side. And the reason is because this altitude is the shortest distance between this black line and this red line. The altitude, the yellow, is the shortest distance between this black and red line, and it retains that distance the whole time And we know that this is 90 degrees because it's part of the altitude of the triangle, and the altitude of this triangle has a perpendicular relationship with the base. But we also know that since this line is parallel, well, this is 90 degrees as well. This is 90 degrees as well. This is 90 degrees as well, okay? So whenever you have two segments or lines that are perpendicular to this yellow line, the same line in between them, well, those lines are parallel. So this red line is parallel to this black line, which means the slope of the red line must be the same as the slope of the black line. And let's go ahead and find the slope of the black line. So the slope of the m sub b for black line would be, of course, y2 minus y1 all over x2 minus x1. And that turns out to be, I like parentheses, so we're going to use parentheses here. We're going to call this x1 y1, and we're going to call this x2 y2. So y2 is 2, y1 is 6, x2 is 8, and x1 is 0. And that right there turns out to be most definitely negative 4 all over 8, which reduces to negative 1/2. So that's the slope of this black line. Seeing as how the red line is parallel to this black line, then we know for a fact that the slope of this red line is also negative 1/2. So that's how you do problem number 52. So problem number 53 is an arithmetic sequence and an arithmetic series problem. So very quickly, arithmetic sequence formula is this, and this is definitely worth writing down. This is definitely worth getting familiar with. Now, basically, what this means is, first of all, what is an arithmetic sequence? Basically means you have some starting number, and then maybe this goes up by 4 every time. So it goes 3 to 7, 7 to 11, 15, and 19. Okay, and maybe it goes on forever. So that's how you know it's an arithmetic sequence. When there's the same difference between each of the numbers in the list, that's an arithmetic sequence, rather. Hopefully I said sequence. And the difference between each term in the sequence is what we call D. So in this case, it's 4, and that's what we would call D. Now, you might be wondering, what does n mean? Well, n means, like a sub n means the last term in this sequence. That's basically what it means. So let's say we wanted to find like the 50th term in this sequence. Let's say we kept going here, and we have 1 underlined, 2 underlines, 3 underlines, 4 underlined, 5 underlined, all the way to 50 underlines. Well, if we wanted to find out, well, what is the 50th term? What's the blue number that's situated above the 50th red underline? Well, then we would find a sub 50, and then 50 would go here, actually. 50 would go here, and then it would be a sub 1 plus 49, because 50 minus 1, 49 times 4. So that leads to the next question. Well, what is a sub 1? Well, a sub 1 is always the first number in the sequence, okay? So in this case, a sub 1 would of course be 3 itself, okay? Now, obviously, this is something that would take a lot of practice to get the hang of. So for those of you watching, hopefully you have some good supplemental material to study when it comes to the arithmetic sequence and the arithmetic series. But this is the formula that would enable you to find the nth term in the sequence. Again, if you wanted to find the 50th term in a sequence, well, you're going to find a sub 50, and this n would be 50. This is the first term, and d represents the difference between each term in the sequence. Now, that's a nice formula. Another formula that you need is for the arithmetic series, where we could denote that with an s sub n. And what that is going to be n over 2 times a sub 1 plus a sub n. Now, what is a series in the first place? Well, as you may recall, before we just worked with a sequence that had 3 as a number, and then it really just kept going, where it was 3, and then it was 7, and then it was 11, and then it was, I believe that was 15, yeah, and then 19. And there was a difference between 4. The difference between each term is 4. And a series is when you take a list, when you take an arithmetic sequence, but you add all the numbers. So a series would answer the question of what would happen if we added all the numbers up to a certain, up to a certain point. So if n was 50, uh, then s sub 50 would help you figure out, well, what's the sum of all the numbers in the sequence all the way up to the 50th term? Okay, so that is the formula for an arithmetic series. Okay, so a sequence is the list of numbers where the difference between each term is the same, and a series is the sum of all the numbers in an arithmetic sequence up to a certain number. Okay, so hopefully that makes sense to you guys. Now, with regards to this particular problem, the reason, of course, I'm going over this is because this problem is a problem that features both of these formulas, and you're going to see why in a moment. Now, apparently, on this person's first day, he made 24 calls, so I'm actually going to write that right now. Okay, and we're going to have these sort of underlines representing each day. And his goal is to make 5 more calls on each successive day than he made the day before. So, for example, on the next day, he's going to make 5 more calls, which is going to put him at 29. And then after that, it's going to be 5 more calls, which is going to put him at 34. 5 more calls after that puts him at 39, and so on. Okay? Now, as we can clearly see the difference between each of these numbers is 5, right? It's plus 5. Plus 5, plus 5. So we are most definitely dealing with an arithmetic sequence in this case. So let's see, if Marshall met but did not exceed his goal, how many calls had he made in all after spending exactly 20 days? So basically what we want to do is we want to add all of these numbers up to 20. To the 20th term. So you can imagine there's 20 of these blue underlines, and we want to add all the red numbers up, and that's the answer. Well, that is going to be a lot of work. That's going to be a lot of time in your calculator, which is why these formulas are amazing at saving time. So ultimately, we're going to be using this one because we're adding all the numbers up, and this is the formula that pertains to adding. Now, let's actually start to work with this formula because we know we're going to use it anyway. So let's see what we can fill in at this point. So, for example, we know that it's going to be S sub 20 because there's 20 terms, 20 days, right? There's 20 days that we're taking into account, and we're adding the calls he made on each of those 20 days. So there's 20 days going by. And we know that n right here is also going to be 20. So we're going to write 20 over 2. By the way, we also know the first term. The first term, a sub 1 is the first term, right, which goes right here. Well, we know what a sub 1 is. It's 24. That's the first term. So we're just going to put that there. And then it's going to be plus the last term in the sequence, a sub 20, the last term in the sequence. Now, we do not know that, so I'm going to write a sub 20 because we don't know that. In fact, I'm going to write it in blue to really draw attention to it because that's the thing that we need to find in order to figure out what the answer is. I mean, this is the answer, but we need a sub 20. So the question is, oh, well, how am I going to get a sub 20? Well, guess what? That's where this thing comes in, okay? That's where the sequence formula comes in. That gives you a sub 20. In other words, that gives you the actual red number that's on top of the 20th blue underline. You can imagine 20 blue underlines And the red number that's on top of that 20th blue one, we could find that by using this formula. So that's what we're going to do right now. We are going to bring this formula into play. We are going to find a sub 20 by just kind of going through the motions. It's a sub 1. Well, we know what a sub 1 is. It's 24. Plus n minus 2. That's going to be 20 minus, n minus 1 rather. That's going to be 20 minus 1 times d. Well, what's d? D is the difference between each term, so that's going to be 5. Now, I'm going to save room on the whiteboard by just kind of doing these calculations somewhat with you right now. 20 minus 1 is 19. So this is going to be 24 plus 19 times 5. PEMDAS would have us multiply 19 times 5 first, and that is 95. And it's going to be 95 plus 24, which is 119. So a sub 20 turns out to be 119, which means I could replace this a sub 20 with 119. So on the next line underneath, we're going to do a little bit of calculating. So 20 over 2 is just 10. And it's going to be 10 times 24 plus 119. PEMDAS says that we should add the parentheses first. So 24 plus 119 is 143. So we will bring this down one more time. So it's really going to be 10 times 143. And that, of course, turns out to be 143, only with 2 zeros tacked onto the end of it, because that's what you do when you multiply things by 10. Well, actually 1 0, pardon me, 1 0 tacked onto the end of it. So this would be 1430, also known as 1430. And that is the answer, which is answer choice D. So that's how you do that one. I would definitely familiarize myself with both of these. Remember, this has to do with just the sequence, which means the list of numbers. This one has to do with what happens when you sum all of those numbers. Those numbers, when you add them all together. That's this one. Problem 54 is a piecewise function problem. And the final question is, which of the following is the graph of the function f of x defined below? So they give you a piecewise function, and then they want you to tell them what the graph of that piecewise function is. So I'm going to write the piecewise function right now. So essentially, this is the piecewise function right here. Now, when I deal with piecewise functions, what I like to do is pay very close attention to the critical values. And what I mean by critical values are these boundaries here. So basically, x squared minus 2, which by the way is a parabola, that's the graph when x is less than 1. That's a critical value of 1 right there. The linear function of x minus 7, well, that's the graph when the x values are between 1 and 5. So 1 is already a critical value, but 5 is a critical value, and then 5 is represented there as well. So what I like to do is actually just sort of take note of these critical values. And I even, on my scrap paper and you on your test pamphlets, if you want to, you could write these dotted lines, because these vertical dotted lines are where the graph changes, okay? Now, let's investigate the top row. It says x squared minus 2. Well, first of all, it's a parabola, because, anytime you see that degree of 2, then it's a parabola. We have the highest exponent is 2. And not only is it a parabola, but it is an upward-facing parabola, because the leading coefficient is a positive 1. Okay, so the fact that the leading coefficient is positive means that it's upward-facing. And this minus 2 means that the parabola has been shifted downward 2 units. And this parabola apparently is taking place on this graph for all the values where x is less than or equal to 1. So I'm actually going to draw that. I am going to draw that right now. Now, let's just be very clear, though. What's happening when x is 1? I mean, we know for a fact that the parabola, it's shifted down to -2, right? I mean, we know we're going to have a parabola that looks kind of like that, right? But I'm curious, where is the parabola when x is actually 1, right? And the way to do that is you can actually plug 1, the x value of 1, into this and find out what the y value is. Now, when x is 1, that would be 1 squared. I'll even write that. It would be 1 squared minus 2, and that equals -1. So we know that this parabola goes through this y value of -2, and then it makes it up here, corresponding with this y value of -1 here. Now, I'm not going to write -1 because it might get a little messy on the screen, but you can imagine it's just a parabola that goes down. Now, it would keep going, but according to this information, the parabola is only taking place for all x values less than or equal to the x value of 1. Well, the x value of 1 is right here, and it goes all the way, cuts through that y value of -2, and then it hits that point. And I'll even denote what that point is. That point is 1 comma -1. All right, that is this point right here. Now, I just want to say that we are done because there's only one answer choice where this is true, and that is answer choice K. Okay, there's only one answer choice where this parabola is represented, and that is answer choice K. Now, answer choice J looks kind of close, but notice how the end point, the right-hand end point of the parabola in answer choice J, well, that lands at the point 1 comma 0. That's not what we want. We want the right-hand end point of this parabola to land at 1 comma -1. Now, some of you might be wondering, it's like, okay, great, we just saved ourselves time, but how would I graph the rest of this thing in case I had to? Well, the bottom line is what you would do is you would notice that the second row is a linear equation with a positive slope of 1 over 1. Okay, so don't forget that there's a positive slope of 1 over 1, and it's got a y-intercept of -7. So that means that it would, under normal circumstances, if it wasn't a piecewise function, under normal circumstances, it would definitely be a line that goes through, -7, and it would go up like that. But this line is only taking place between the x values of 1 and 5. So yeah, hypothetically or theoretically, it would cut through that, but it only would actually start here and then go up. So that line would look something like this. Now, let's be very clear. It's x is greater than 1 and less than 5. So that means as it pertains to the partition, you'd have this open circle and an open circle there because this line is between these values, but it doesn't actually hit these values. And the way to communicate that is to have that open circle there, okay? Now, as far as this one, the third line goes, I would say the best way to rewrite that is to flip it around. That's my little curly Q arrow. So it's -x plus 4, because this is annoying looking. We're going to want to flip that around so it looks a little bit more like what we're used to. That's a -1 over 1 slope times x plus a y-intercept of 4, so it's a negative slope. So that means it would start up here somewhere. It would go down, right? But it wouldn't start until x is greater than 5. So it would start here hypothetically, but it goes down, 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 and then it only starts after the x value of 5, and then it cuts through like that, and it would look something along these lines, where it would be, I'll use yellow, it would be something like that, okay? So that's how you would get a sense, at least, of what the graph looks like comprehensively. But again, notice how all we needed to do was meticulously tend to this first row, and we had our answer. So once again, the answer is K. So the quick way of solving problem number 55 is to just simply be aware of the permutation formula. And the permutation formula is as follows. You have P with an N here, an R here, N factorial all over n minus r factorial. Now I am going to describe what all this means soon, but this is the formula, and it does benefit you to just sort of remember this. There's also a combination formula, which I could talk about in a little while. But this is the permutation formula, and what this basically says is that this is the number of permutations of n objects taken r at a time. So this is the permutation of n objects taken r at a time. So problem number 55 is asking for the expression that would describe this scenario. And then you would just fill in, the cast of characters into the expression. So this would become 15 factorial all over. Looks like it would be 15 minus 5 factorial. Now, some of you might be wondering, well, what the heck is all this? And that is an understandable question. So first of all, let's begin with this symbol right here, this exclamation point symbol. Very quickly, all you need to know is that basically, imagine we had 10 factorial. What that means is anytime you see a number with an exclamation point after it like that, it just means take the number and write it down. And then multiply it by the number that's right underneath. And multiply that by the number that's right underneath. And multiply that by the number that's right underneath, all the way until you get to 1. And then you are finished. Okay, so actually 10 factorial, as you can see, would be a pretty big number because it's 10 times 9 times 8 times 7. Okay, so that's all it means. Now, obviously, another example would be 2 factorial. Well, that's actually a little easier, right? That's going to be 2 times 1, and then you're done. Clearly, that equals 2. I will also mention that, interestingly enough, 0 factorial equals 1. Okay, so that's kind of like the only weird one. All of these other ones are a little bit more straightforward. Now, you might also be wondering, what is a permutation? Well, a permutation is a way to figure out all the different ways that items or people or objects can be ordered. And for example, imagine you had the letters A, B, C, and you want to investigate how many different ways can we order these 3 letters. Well, you might move to a CB. Then you might try BCA, and then BAC, and then you might try CBA, and you might try CAB, and that would exhaust the list. But imagine you maybe didn't even want to know what the different orderings were, but you wanted to know how many there would be. Well, this is where the permutation formula would actually come into play. So, for example, you could have seen this situation as how many different ways can we order 3 objects taken 3 at a time. So it's kind of a simple version. You want to take 3 objects taken 3 at a time. Well, that would be 3 factorial, right? Because that goes on top. And then underneath, it would be 3 minus 3 factorial. And therefore, it would be 3 factorial all over 0 factorial, which is really simply 3 factorial over 1. Because as I said before, 0 factorial is just 1. So that means I can sort of dismiss this 1, if you think about it, because really every number has a 1 underneath it in the denominator. So this would give me the amount of different orderings of 3 objects taken 3 at a time. So that would be 3 times 2 times 1, and of course that is 6, okay? So that's a quick lesson on permutations. Now, I don't want to get into what a combination is, but I will briefly introduce you to at least the formula for a combination. Now, this is the formula for a permutation. You might get a similar question talking about combinations. And the combination formula is kind of similar, actually, where you're going to have n factorial on top, but then underneath, you have the same thing, only there's this extra letter, this extra factorial. Now, again, I'm not going to get into that, but I did want to throw it in there because, as we could see with problem number 55 on the ACT, it really just benefited you to know this formula. Even if you're not particularly well practiced at, working out permutations, it still benefited you to know it, and you can very quickly see what the answer is upon simply knowing the formula. And in the advent that you're going to have a combination problem on the ACT, it's good to know the combination formula. You might have a very similar problem, only instead of a permutation, they're going to say combination, and in which case, just know it's the exact same thing, except you have a little bit extra on the bottom. We could put it that way, okay? Where it's this number, so this would be n objects taken r at a time, well, the r would be here. So that is problem number 55, and the answer is D. So problem number 56 requires an awareness not only of imaginary numbers, being at least somewhat aware of the imaginary number I, but it also requires an awareness of conjugates, which sort of requires an awareness of the difference between two squares, okay? So I know I said a lot. Let me just remind you of something. And I know this seems unrelated. It's actually not. Many of you have learned a squared minus b squared equals a minus b times a plus b. Okay, so that means if you had something like x squared minus 25, well, that would be x minus 5 times x plus 5. Okay, so many of you are aware of that. You've seen that kind of thing before. Now, what I'm going to do is I'm going to actually just leave that there as a reference for us. Okay. And we're going to kind of draw upon this later. Now, clearly what we're dealing with is the following expression. You have I over radical x minus I. And then they say, which of the following expressions is equivalent? So you have this whole list of answer choices that may or may not be equivalent, and it could be a little confusing, obviously. Now, what would be helpful is remembering that, number one, don't freak out about I. It just means the square root of -1. And in fact, the ACT is kind enough to remind you of that. I would also add, it's nice to remember that I squared, therefore, is -1. So in my opinion, at least as it pertains to this problem, these two pieces of information are crucial, because doesn't it make sense that if I equals the square root of -1, well, squaring that would give you just a -1. So we'll leave that as a reference too. And we brought it up here. So as it pertains to the actual problem, those of you who have at least some experience, simplifying rational expressions where you have a radical in the denominator or even an imaginary number in the denominator, you may have learned that mathematicians decided at some point that they do not like that. They don't like it when either a radical is down there or an imaginary number is down there. And there's various ways of ensuring that the final expression, the final simplified expression for something like this, would no longer feature a radical in the denominator and or an imaginary number in the denominator. Now, in the case of a binomial like this in the denominator, one thing you can do is you can multiply the denominator by what is called the conjugate. And the conjugate is literally the exact same thing, except you are changing the operation in the middle to the opposite. So if this said plus, then it would be minus here. Now, you're going to see why we do that in a moment. But let's just remember, I'm not allowed to multiply the bottom by some number. I mean, this is just some number. I know it looks weird, but it's just some number. I'm not allowed to multiply the bottom by some number unless I multiply the top by the same number. That's like the rule, right? When you're manipulating fractions. Now you might be wondering, okay, great, why did we do this? You know, what's the point? Well, the point is because if you look only at the bottom, what you will see is that we have a difference between two squares scenario. It is the exact same structure as this, okay? Now, most of y'all are used to going from a squared minus b squared and factoring it and turning it into that. So most of you are probably familiar with moving from this direction to this direction, but occasionally it's going to be helpful to move from this direction into this direction. And that's what we're going to do right now. So when we do so, what happens as a result is we'll focus on the denominator first. This is going to be radical x squared minus I squared. And if you have any doubt about that, just look at what happened here. This became a squared minus b squared. What was a and b? Well, a is the first number, b is the other number. Well, this is the first number squared minus the second number squared. What was the first number? Radical x. What was the second number? I. So there you go. Now we're going to deal with that in a moment. Let's work out the numerator now. So what we'll have on top is just I times this entire quantity, and many of you know you could just distribute it. So it'll be I times the first term plus I times the second term. And that works out to be I times radical x plus I squared. So we're making a lot of headway for sure so far. Let's keep simplifying this situation. Now, do you remember how I told you that I squared equals -1? That insight's going to be really helpful. So on the next line, we still have this I radical x. We're kind of stuck with that. But let's take a look at this one. We have plus I squared. That's plus -1, also known as -1, right? So I radical x plus -1, therefore it's I radical x minus 1. Down here, anytime you square a square root, it cancels the square root out. So the exponent cancels and the square root symbol cancels, not the x, but the square root symbol cancels, leaving us with just x. And then over here we have minus I squared. Well, we already talked about how I squared equals -1. So minus I squared. I squared is -1, so it's going to be minus -1, also known as plus 1. So you do have to be careful with the signs. We are subtracting -1. So we're adding 1. And that leads to the answer, which is K. That's the answer. Right there. The answer is K for that one. I'm going to cut to the chase with problem number 57. There's a lot that we could say about vectors, but I want to just give you a quick way of solving something like that, because it's not like the ACT is going to get too deep into vectors. What you have to have is a general idea of what to do. Now, let's just be very clear. Imagine I had a vector that was like this, okay? Now, I just want to make clear that this vector right here that hits the point 2, 1 right there, that would have a vector notation of 2, 1, where the first number tells you how much it's going over, and the second number tells you how much it's going up. Now, another way of writing the exact same information is by using the unit vector notation, which would be to rewrite what I just wrote as 2i plus 1j. Okay, I'll write 1, even though in reality we wouldn't really have to write that 1 because it would just be j. But I just want you to understand that this is one way of talking about the activity of a vector, and this is an equally valid way of talking about the activity of a vector. I do want to note that this vector is placed in such a way that the endpoint is on the origin, but this vector could be represented anywhere in space. It could be represented, for example, here in space. And even if it was represented here, it would still have this same notation because the notation only really describes like what it's doing from its beginning location. So it's still going over 2 and up 1. Okay, so just because something has the notation of 2 comma 1, it doesn't mean that it's positioned necessarily on the origin. Okay, now let's say that we wanted to add another vector though to this vector. Okay, well, let's say that that vector that we want to add was 3 comma 7. Okay, now I'm not going to draw 3 comma 7 because in my opinion with problem number 57, even though they give you a visual, you don't really need the visual. You really just need to know how to add this stuff. Okay, now it's actually pretty easy. I think a lot of you are going to be happy with how easy it is. It's very intuitive actually. And let's make a mental note that this could also be rewritten as this in the exact same way. Okay. Now, the question is, how do you add these two? Well, super easy. We're just going to set them up right now so that we can add them. And all you have to do is add the first two values, 2 plus 3, and it's going to be comma 1 plus 7. That's all you have to do. And then that ends up becoming 5 comma 8. Okay? So that's going to result in a vector that goes 5 over and 8 up. Now again, you could think about the visual if you want to, or you could just understand the protocol and understand that that could be rewritten in the following form. That could be rewritten as 5i plus 8j. So that's good to know. So how does that apply to our problem? Well, it applies because they give you two vectors and they're saying, oh, we're adding CD to AB, right? Well, let's figure out what is the component form or what is the notation for AB. Well, if you look at AB, which is the larger of the two vectors, you can clearly see that it goes over 9 and it goes up. It looks like it's 6. So if you look closely at the first vector, which is vector AB, it goes over 9 and up 6. And we're going to be adding that to another vector that goes over 0 and up how many? 1, 2, 3, 4, 5. So guess what? Adding these is going to be a piece of cake. Okay, I'm going to write an equal sign. That's literally going to be 9 plus 0 and 6 plus 5. And that, of course, would be 9 comma 11. And as I said before, you could always just rewrite that as 9i, that's a 9, plus 11j, which is the answer, and that is E. So in problem 58, they give you this formula that says the time it takes for a full pendulum swing is modeled by this equation right here. And kind of a weird looking formula. But this is time, and this has to do with the length of the actual string in the pendulum. And according to them, the time required for a complete swing of pendulum 1 is triple the time required for a complete swing of pendulum 2. So what I would like to do is just write T1, because that's the time required that the pendulum takes to swing for pendulum 1. Apparently that equals 3 times the time required for a complete swing of pendulum 2. So I'm going to write 3 times T2, where T1 represents the time required for a complete swing of pendulum 1, and T2 represents the time required for a complete swing of pendulum 2. Okay, and they give us this information. Now I'm just going to write that down because I have a feeling that's going to come in handy soon. Okay, now they are asking, finally, the length of pendulum 1 string is how many times the length of pendulum 2's string. Okay. Now, since we're sort of working with the length and comparing one length to the other length, I have learned through experience that it can be helpful to rearrange the equation they give us and solve for L, because L, what we're doing is comparing the length of the first thing to the length of the second thing. So let's get a sense of what L equals just in general in terms of all this other stuff, okay? Now, the way to do that is to recognize that, well, we want to solve for L, so let's at least get this square root by itself. So we got to get rid of the 2 pi. And the way to do that is to divide both sides by 2 pi. And as a result of that, of course, we can cancel these, right? And then we end up with L, radical L over 32 equals T over 2 pi. And don't freak out, this is just 6 point something approximately, right? And then we have this scenario. We still want to solve for L, so we have to get rid of the square root symbol now. And the way to do that is to square both sides. Okay, so we're going to now square this side and this side. And as a result of that, the exponent of 2 cancels the square root symbol, not what's underneath, but just the square root symbol itself. And that results in L over 32 equals the square, well, T over 2 pi squared, I should say. Now, at the end of the day, we're still trying to solve for L. So therefore, what we could do now is multiply both sides. We'll keep it over here. Multiply both sides by 32. And in doing so, we, of course, cancel these 32s. And we have L equals 32 times T over 2 pi. So at the end of the day, we took the original equation that they gave us, and we just rearranged it so we could really focus on what L equals. Now, what I want to do now is something similar to what I did here. Remember, T1 represents the time it takes for pendulum swing to do a full, complete swing, and T2 represents the time required for a complete swing of pendulum 2. Well, I want to kind of represent L1 and L2 as well. So what I'm going to do is rewrite this equation twice. I'm going to write an equation for L1 and T1 and another equation for L2 and T2. So I'm going to do that right now. So we're going to have an equation for L1, and that's going to equal 32. I'm just, putting the L on the left and the rest of it on the right. That's going to equal 32 times T1 over 2 pi squared. I'm also going to write L2. L2, which is the length of the second pendulum, that's going to equal 32 times T2 over 2 pi squared. So You might be wondering, well, where am I going with this? Well, remember, the final question is the length of pendulum 1 string is how many times the length of pendulum 2 string. So we want to know the length of pendulum 1 string is how many times the length of pendulum 2 string. So what you got to do here is focus on the length of pendulum 1 string, okay? Because that's what the question has to do with. So we're going to focus on this, okay? Now, what we're going to do is we're going to replace this t sub 1 with 3t sub 2 because we already, made the mental note or even the physical note that t sub 1 equals 3 times t sub 2. The time required for a full swing of pendulum 1 is 3 times the time required for a full swing of pendulum 2. So what we're going to do is just kind of continue to work with this equation here. So really, it's 32 times 3t2 sub 2 all over 2 pi squared. And I decided to move the equation for L2 over here just to give myself some room, but it's still there, right? So we already, we have L1 equals this, L2 equals this, and, we have a different time here and a different time here corresponding with L1. But as I said before, t sub 1 is really 3 times t sub 2, so you could substitute it in there. Then what we could realize is that this exponent, I mean, really we could apply it to everything inside here. But what I'm going to do is apply the exponent only to this 3 and make it a 9, and I'm going to leave the rest of this stuff inside parentheses raised to the 2nd power. So what I mean by that is this 3 secretly becomes a 9. And what we could do is we could take the 9 outside of the whole thing. Okay, now in case that's not clear, just know that if I had A, B, and C raised to the 2nd power, the reality is that that could be rewritten such that since it's a product raised to a power, you could rewrite it as A squared, B squared, C squared. And you can also write it as A squared times the product of BC squared. Because just like in a way I sort of applied the exponent to each of these to go here, well, I could once again just apply this exponent to these two to bring it back up here, right? So these are all equal. Now, in a way, what that means is that I could really just take something that looks like this and pick one of the factors, such as A, and sort of extract it on the outside of parentheses. As long as I square it, I can extract it on the outside of the parentheses while leaving BC in there. Okay, so that's sort of a general demonstration of the principle involved here. So how that applies for our particular purposes is that we could extract a 3 squared out of this whole thing. And that's what we're going to do. Now, when I extract the 3 squared out of this parentheses, I know from experience that I'm going to want that to be on the outside. Okay? Now, 3 squared, by the way, is 9. So what we're going to do is we're going to write that 9 over here. And the rest of everything, I'm going to actually wrap in brackets. And it's going to be 32 times just t sub 2 now, right? Because we took the 3 squared out, squared. Okay, now I used brackets only to just kind of highlight the fact that I extracted the 9 all the way on the outside. And the truth of the matter is, it's just 9 times 32. I mean, I could simplify this if I wanted to. 9 times 32 is, I don't know, 270 plus 18, right? 288 or something. So I could do that, but for the purpose of this problem, I actually don't want to. And here's why. Here's why. Because think about it. This is, this is all L1. What we've just realized is that the length of the first pendulum, of pendulum 1, is 9 times whatever the heck this is. 9 times whatever this is. Well, what is this? this is this, right? This green bracket is literally L2. So you know what? I'm just going to write that. Because what we have going on here is 9 times L2. So in other words, the length of pendulum 1 string is 9 times the length of pendulum 2 string. That's how you get the answer to that one. A bit complicated, something that requires practice for sure. Hopefully you understand it. The answer, therefore, is J. The answer is J for this one. There are various laws of logarithms that are important to know. There's a lot to say about logarithms, but I'm only going to talk about something called logarithmic expansion, okay? And what that basically says is, I'm going to provide just a separate example just to illustrate the principle first, okay? So this is not the actual problem, but this is a principle. So if I had log of some product A and B, well, the truth is that I could expand that to log A plus log B. So that's a principle that's very, very useful. In fact, we're going to put that over here. So we're going to remember that, okay? We're going to remember that. Also, it helps to know that if I have log of some number x right there, but it's raised to a power like b, all right, some power called b, well, what I could do is I could bring that exponent of b all the way out front. It's kind of an interesting thing. And rewrite it that way, where it's b times log of just x now, okay? Now, this b is no longer an exponent. It's actually like a coefficient of log x, okay? It's a number that's currently being multiplied to log x. So that's a principle that's very important. It turns out that these are the only two principles you really need to know for this particular problem. So I'm just going to move everything over here. We're going to use that as a reference as needed. So apparently, you know, they tell us, they're like, oh, log sub ax, log with a base of a, x, well, that equals s. And they also say that log with the same base of a, y equals t. So in other words, anytime in the future you see log with a base of a, x, it's really just s. Anytime you see log with a base of a, y, it's really just t. And then they go ahead and ask you the question, well, what is, you know, log with a base of a, xy squared? Well, the big picture is that you just have some number. I know it's a product, but it's just some number squared. So really it's this green principle that we're going to want to employ because we have some number squared. You always start from the outside in, at least when it comes to these, okay, these kinds of problems. So you're going to apply that principle first. So the first thing we could do is take that exponent of 2 and just stick it out front, okay? And then we have that, okay? Now, let's keep in mind, it is 2 times this entire log of xy. So just to remind myself of that fact, I'm actually going to draw brackets around this because it's important to remember that it is indeed 2 times the entire log xy. Now log xy, I understand some of you might be confused, but just know, I mean, it's just a number. It's going to turn out to be some number. I mean, if we knew the variables, then it would just turn out to be a number, so it's going to be 2 times that number, okay? Now, inside the red brackets, we can clearly see we have log of a product. Well, what do we do when we have log of a product? Well, you split the 2 logs apart, and to be thorough, let's keep the base here. These principles only apply if the base, by the way, is the same, just so you know, Okay, I should have mentioned that before. Nonetheless, we have a base of A, so everything checks out. It's all the same. So now on the next line, we're going to apply the top principle here, and therefore we are indeed dealing with 2 times. Now I'm going to keep the brackets. It's going to be log with a base of A x plus log with a base of A y, close brackets. Okay? Because remember, this bracket just expands and turns into this, and we still have 2 times this whole thing. Okay? Now, let's be very clear. Log with a base of ax is s. Log with a base of ay is t. So we could totally replace that. Substitute in s plus t inside of there. S and t with a plus in between them. Okay? Pretty simple, right? Obviously it takes practice, but the concept itself is not too bad. And actually we're done. That is answer choice A. Now it so happens that I used brackets, but they're using parentheses. And that is fine, totally fine. I would be on the lookout, let's say there wasn't 2 times the quantity of s plus t. I would be on the lookout in the answer choices for an answer choice that has 2 distributed, 2s plus 2t, and that would be the answer. But it turns out answer choice A just has it in this form, and that is fine. So the answer is A. So the final question in problem number 60 is, by what percent did her best long jump distance increase from 1990 to 1992? And this is clearly a percent increase problem, and you're going to have some awareness of percentages. Let's get clear that in 1990, this person had, Jennifer, had a best long jump distance, and she also had one in 1991, and she also had one in 1992. And apparently in 1991, her best long jump distance increased by 10%, and then from there it increased by 20%. So most students would probably make the mistake of just adding 10% plus 20%, but that's kind of the classic mistake that you're going to want to avoid. Now, this is a good example of a problem where you might want to bring it down to earth, and if it's a percentage problem, you might want to make your base amount 100, okay? You're allowed to do that as long as they don't actually specify the best long jump distance. So let's say that in 1990 it was 100, and that increased by 10%. So in 1991, you can kind of do that in your head, where 10% of 100 is, 10. So we're going to add 10 to 100, giving us 110. But then from there, it increased by 20%. So let's figure that out. If we want to know what 110 is increased by 20%, well, in reality, it's 110 plus 20% of 110. Okay, now you may have noticed I represented the percentage as a decimal. Often, well, really always, I would say, when you're doing calculations. Well, let's say almost always. You're going to want to use a decimal instead of an actual percentage. So in this case, it's going to be 110 plus 0.2 times 110. So that's going to be 110 plus 22, and that will equal 132. So sort of wrap that in green. That's going to go right there. So again, the final question is, by what percent did her best long jump distance increase from 1990 to 1992? So from 100 to 132, what percent increases that? Well, that is a difference of 32 units. from 100 all the way to 132. Well, that's a difference of 32 units. So the question is, 32 units is what percent of 100 units? Well, that's easy. 32 units is 32% of 100. And in case you needed to sort of see that in a sentence form, the question was 32 is what percent of 100. So it really kind of depends on how you learn to navigate these percentages. You could do is over of. I mean, that's a common way that teachers often teach their students how to navigate answering questions like this, where the number that's to the left of the word is and the number that's to the right of the word of are taken into account, and you just simply remember, is over of equals the literal percent, not decimal, but the actual percent over 100. And in this case, that would be 32 over 100 equals what percent over 100? Well, this one is easy. We don't even really have to cross multiply because this says something over 100 equals something over 100. So this percent must be 32. So the answer is 32. And that is F. Answer choice F. So I'd like to reiterate the key insight here is if they say, oh, it's a 10% jump from the old number and then it's a 20% jump from there, you do not want to add the percentages. It's not going to be 30%. It's going to be 10% increase of the first number and then 20% increase of that number brings us to 132. So you do have to sort of map things out, figure out, okay, well, what is, 20% of 110, and then add that to 110. Then we have our new amount, which is 132. And then you would compare, at least in the case of this problem, you'd be comparing the original amount and the final amount, and that is a 32% increase upon the original amount.